Dear colleagues, good morning. We are starting the last day of our conference, but uh, we would like to ask for a slight delay, maybe 15 minutes, because of the situation during the night. We're still waiting for the participants to arrive and to connect. So I hope it won't be the problem if we delay a little bit. Thank you.
Okay. Hello, Sim. Distinguished participants, colleagues, and guests and partners, it's a great honor to me to welcome you to the closing day of the 9th International Material Science Conference, HighMatTech. A busy week is coming to an end, during which we discussed breakthrough across the 7 main areas of material science, from metals and alloys to optical materials, nanotechnologies, and hydrogen material science. Today, we conclude our work with a symposium dedicated to advanced composite materials. And let's start our symposium. The first speaker with keynote, Maxim Yurchenko. It's a professor from Patton Electric Welding Institute with keynote speech, Advanced Biopolymer Composites for Medical Applications. Please, Maxim, let's start.
Morning, colleagues. I'm not saying good morning, morning. Tell me, please, do you see my workspace?
Still not.
Just a second. And now?
All is okay. You can start.
Okay. Dear colleagues, I would like to present the results of 2 projects which are dedicated to advanced biopolymer nanocomposites for medical applications. The first project is Biopol Bone. The project is about implants made with biopolymers, which can degrade inside the human body, and do not need to be unemployed after its application. And the first and the second project is BioPoGen. That is about cryogels for wound healing and regeneration of living tissue. So the first project is about biopol materials. In general, our biopol materials is composite materials with bactericidal action for additive manufacturing of implants and cryogels for wound healing. They're biocompatible, biodegradable, sustainable, and bio-based. Mainly, they're based on 2 materials. That is polylactic acid and polyvinyl alcohol. What's for we are doing that? Traditionally, implants made with metal implants, titanium mainly, and they must be removed from the body after 1 year, 2 years, it depends. In our case, we propose bioimplants made with biopolymers which can biodegrade inside the body and can be removed by itself naturally. We compared our material, polylactide plus, and commercial polylactide filament made for 3D printing. And you may see mechanical properties of both materials, and you can see that the difference is not a big one, but at the same time, we made different investigations, structural, thermogravimetric, differential scanning calorimetry, and so we confirmed using these methods that our materials, they are semi-crystalline, similar to polylactide-based material, but at the same time, we found that it has double cold crystallization. You may see that on the DSC curves. And enthalpy and glass transition temperature and melting temperature, they're same to the basic material polylactide. At the same time, we made mechanical tests of both materials, meaning polylactide-based material and polylactide plus modified by us material, and we found that our material more stable on mechanical properties. Also, we made thermomechanical cycling tests. First, we made polylactide samples and polylactide plus samples using monolithic and perforation samples. And we found that perforated samples are, and our polylactide plus materials, they are more stable and they are close using mechanical and thermal properties to the body, human body. Having calculated temperature relaxation properties, we found that our material and perforated, of course, they're much closer to the human body temperature than other materials. That is very important because all the parts of human body, they are extracting and moved at the same temperature, and our materials and they have these implants have to be perforated. They're much closer to the human body movement than other materials. Of course, we have tested them to by the biophysical properties to the mentioned viruses, bacteria, and even fungi. And we found, so you may see on the slide, the biophysical properties of filament and 3D printed materials, so they work. Of course, we checked the cytotoxicity and genotoxicity, and we found that materials with 0.1% of argentum, they are safe for the human body, but at the same time, materials with 0.5 and higher percents of argentum, they're cytotoxic, and they are not. They cannot be used in such implants or cryogels. You may see here the process of 3D printing of implants for in vivo tests and their modification of their properties and structure. Also, you may see the operation made on rats, and also medical tests, let's say medical tests of the bone growth. So in time, our materials, they bio-destructed, and at the same time bone is grown up. Then we moved further, and you may see the model of implant. It's 3D printing, the modification of its surface, and the final implant you may see on the slide right down, where you see implant with modified structure. The modification of the surface was done with inorganic component for the bone growth and approbation of living tissue. That is real photos made on real body, human body. So model and the first X-ray photo, that is after operation, and in some time, almost 4 months. So the bone grown down and our implant destructed. The second project was dedicated to living tissue regeneration. We made cryogels, and of course we also investigated structure and properties of these cryogels. So you may see here the scheme of cryogel formation. So we mixed polyvinyl alcohol with hyaluronic acid with argentum salt. We mixed it and heated up to 85 degrees during 1 hour. That is made for reaction of argentum formation, of nanoparticles argentum formation. And so you may see that on the photos that our hydrogels, cryogels, they are rather strands to be used as wood healing materials. We investigated the structure of these materials. So you may see here that on the X-ray spectra, that our nanocomposites, they are semi-crystalline compared to PVA with hydroxylic acid, which is absolutely amorphous. We add argentum salt, and we found that after formation of our hydrogels, cryogels, we found absolutely formed nanoparticles of argentum, and our TEM investigations confirmed that. The middle size of our argentum particles are 5 nanometers. That is very important because this surface of argentum nanoparticles, they are very important, since more you have the surface, more they are active, bioactive, instead of bacteria, viruses, or fungi. Since we have cryogels, hydrogels, we are looking for a right name and title of these materials. Of course, these cryogels, they must have some sorption activity, since they have take blood and other things in the wood, from the wood. So we've investigated the influence of formation, the properties of formation of our cryogels on the mechanical properties of cryogels, and we found that increasing the freezing time, the mechanical properties increased, but at the same time, the sorption properties decreased. So it is necessary to optimize the freezing time to get cryogels with good mechanical properties, but at the same time, rather high sorption properties. Also, we investigated thermogeometric properties of our cryogels, and we found that up to 200 degrees, our cryogels have desorption, mainly desorption of water, up to 10 degrees. So the 10%, sorry, 10%. So it means that the water inside cryogels, it is interconnected with our polyvinyl alcohol. Also, we investigated the influence of formation parameters on DC and glaciation temperature and melting temperature, and we found that increasing time of freezing, we found increasing of glaciation temperature. At the same time, adding of argentum salt and formation of argentum nanoparticles, time glaciation temperature decreased, as well as melting temperature. Adding of silver inside our composites increase stress strain dependencies, but at the same time, adding more than 1% of argentum, it rapidly decrease mechanical properties. So we are connected. We connect that with the hydrogen bonding of nanoparticles with polyvinyl alcohol, and but at the same time, increasing of the amount of nanoparticles decreases mechanical properties. So they are more brittle. As if I can say that, they are more brittle with the amount of higher than 1% of silver nanoparticles. Of course, we investigated antimicrobial activity of our composites, and we found that with the amount of silver nanoparticles between 0.1 and 0.5, they have antimicrobial activity, but at the same time, as I said previously, higher amount of silver nanoparticles higher than 0.5 made our nanocomposites toxic. So the main point here is that we have to use amount of nanoparticles between 0.1 up to 0.5. We investigated cytotoxic parameters of our cryogels, and we found that, again, we confirmed, of course, we confirmed that they are not cytotoxic up to 0.5% of argentum nanoparticles. But at the same time, we found that materials with hydraulic acid, they generate growth of living tissue. In parallel, they have a bactericidal effect and not toxic up to 0.5% of amount of argentum nanoparticles. We confirmed that with investigations of living tissue regeneration, and we found that materials with optimized content of argentum nanoparticles and hydraulic acid can stimulate regeneration of living tissue. Here you may see in vivo investigations of effect of our nanocomposites on animal models, rats in our case. So you may see the wound, the beginning of regeneration, and final point of regeneration of living tissue on rat. So using these results, we can confirm that they stimulate living tissue regeneration. Now we are at the stage on in vivo hospitals studies, let's say. So you may see the complex of cryogels sent to hospitals, different hospitals in Kiev, in Dnipro, and in Lviv. So they are now at the stage of testing. So I would like to present our team. So you may see we have different specialists from material science, chemists, physicists, materials processing, and of course, biologists. And our team is representative from representative from 4 institutes of our Academy of Science, mainly from Patton Electric Welding Institute, from Institute of Materials Problems, from Institute of Macromolecular Chemistry, and from Institute of Microbiology and Virology. Thank you for your kind attention, and I would like to answer your questions if you have them.
Thank you, Professor Yuzhenko, for your speech about up-to-date materials and investigations. Dear colleagues, if you have some questions, please ask Professor Yuzhenko. Is any questions? Okay, if no questions, I have some. Dear Professor Yurchenko, you investigate PLA and PVA plastics materials with additives of solid particles. As I know, it's a great problem to distribute homogeneously solid particles in these plastics, and it's influenced on properties of these materials, especially on mechanical properties and some chemical and biocompatibility of these materials. How you solve this problem?
So we used that. First of all, that is very important question. We used water solution of PVA and silver salt. So it is distributed as a dissolved material, and during formation of our cryogels, these nanoparticles are formed. So that is very important point, because they form in the form of both, I don't know, both, due to just difference in viscosity of materials, PVA and water.
And as I understand, you use nanoparticles for PVA, and do you observe agglomeration of these particles in your gels?
PVA we have as a basic material. It is 99% of weight, and salt we used the solution of argentum salt in the form of solution. And while forming our nanocomposites, these nanoparticles are formed. So that is what I am saying, that viscosity of PVA, PVA solution is higher than the solution, the viscosity of argentum salt, formed because of that. They're like oil with water.
Okay, thank you. But I have another questions, because I work in a close field. We work with 3D printing, fused FDM, fused deposit modeling, and we prepare the polymer ceramic compositions. First of all, we have to prepare the filaments for 3D printing. It means that you prepare, using extrusion, you prepare the filaments of composite materials. In your first project, it was PLA and some solid particles in this PLA, as I understand, yes?
Mm-hmm. Yeah.
During extrusion, do you observe some inhomogeneous distribution of solid particles? And how many solid particles you can incorporate in filaments?
Of course, we found not very homogeneous distribution, of course, but the main question was if our composites are active, and they are active. Yes, of course, there is some not homogeneous distribution, let's say somewhere more, somewhere less, but anyway, it is distributed, we say, in normal way. So we have double screw extruder with the most less amount of material is 5 grams. So we can extrude it in a good way, circling, for example, and so on.
Thank you. And I have another questions about your first project. As I understand, you additionally use the hydroxyapatite for your experiments. Yes, it was solid particles in plastic, or it was coating?
It was coated. It was coated in 3 ways, and let's say together with your colleagues from the institute, we discovered that the best coating is made by, we say gluing, but it is not gluing really. It's surfacing using not, for example, plasma irradiation, and not using, for example, it's just solving of the surface, and then surfacing with hydroxyapatite.
Okay, thank you. And
sorry, and the best results after veterinars show that this surfacing is the best. We were surprised, but that is the result of our project.
And I want to ask you about biocompatibility of PLA. As I understand, hydroxyapatite is changed on the bone material. And what about PLA? It's not contaminate the human body because it's incorporated into the human body, and it's had to dissolved or not?
It has to be dissolved. That is the first point. We are just now on the way to investigate it as a result of in vivo investigations on rats. It is dissolved. And the main point why we had to modify PLA, because the speed of biodegradation has to be similar to bone growth. And if it is longer or it is less, we found the problems. So we modified it that in such way when the bone grows, our material destructs, and our material destructs on water and CO2.
Okay, the next question.
Thank you very much, Professor Yudchenko, about your very interesting presentation. Your work is very important, considering how many people are injured and it can save life. And I have one little question. You show your materials, but I didn't see comparison for other company maybe, or you are first line for this problem. I mean, pharmacy company have such many products, and you products you compared with other company.
You mean the first or the second project?
I mean the second project.
The second project. Yes, we have on the market different similar hydrogels, cryogels. It depends on how we can name them, but we found that only our material stimulate living tissue regeneration, because others, they just used for conservation of the wound.
I see. But what about future steps for going to the market for quickly to implementation these materials in medicine, on because now the situation is too bad on the front. You thinking about this problem because it's a very big problem.
Yes, I am absolutely agree with you. That is a big problem. For today, we have a registered trademark. That is the first step. So BIPO materials, that is registered trademark. And now we, let's say, help our surgeries with our materials. At the same time, we are at the step of registration as a material for I'm not able to answer which way material, because that is really not for medicine. That is for beauty, for the beauty, let's say.
Okay.
It is much simple than to register it them for the medicine.
I understand. Thank you very much for your work. I wish you good luck and more quickly to register your materials, because it's really helpful for many, many people. It's very important things. Thank you.
Thank you very much for your mind.
Okay, thank you, Professor Yurchenko, and we continue our session. The next speech will be from the same Patton Electric Welding Institute, together with Institute of Macromolecular Chemistry. Alexey Maruzhenko, resistive implant welding of plastics using thin film polymer composites. Mr. Maruzhenko is okay. Offline. Oh, it's quite good in our time, especially from this situation. Please.
Yep. Everyone, small check. Whoa. Yes, that's me. And yeah. No, it's okay. Just checking the stool. So firstly, I would like to thank committee for opportunity to present our research, and also I would like to emphasize the input of teammates who make and I hope will make a great input and impact in general to this topic. So without them, without you, it will not be possible to present it today. And the topic, the title of this presentation is about welding, resistive implant welding by thin polymer composites. A few words about resistive implant welding. It is quite well-known technique. Usually it involves power supply, heating element, and welding parts, obviously, and in accordance with some electrical properties and needed procedures, the weld can be produced. So the main advantages of this method is fusion-based joining. It means that parts are polymer matrix, since usually it is the one type matrix. They are blending, and it makes much greater mechanical properties. Secondly, it is cost efficiency, because this process can be can be automatized and put on the line. It means that all steps and stages can be precisely scheduled. And the last one, versatility, means that this method, this technique of welding can fit different surfaces. And not only like flat surface, but also with some complex shape. So in this field, in our department was made some impact. The main topic, the main issue for me personally was that approach that was based on polymer composites as well. It was used for quite thick materials, thick samples. And the last point, versatility or flexibility, is not cannot be applied to this approach with thick samples. So that's why we decided to move further, and we made samples with much thinner samples, approximately 200 microns. So generally, films was made firstly with some structure. It called segregated structure because we needed lower percolation threshold. It will be discussed further, but it was a decision to make such ordered organization of the filler. So generally, high density polyethylene granules for extrusion, for pipe extrusion, they are normally pre-filled by approximately 2 mass percent of carbon black was grinned, sieved, and the fractions, several fractions were obtained. We worked with the fraction approximately from 100 to up to 200 microns. It was a normal distribution. Again, we will discuss it further, but it will correlate with the thickness of the film. So in polymer, in polymer powder was added fillers. In our case, it was a mixture. Firstly, we introduced carbon filler as nanotubes mixed, and then carbon black, because it was a much bigger amount, and for better distribution, it was a consequent stages. Then the final mixture was hot compacted in the hot press, and quite a big area of sample was obtained. It gave us an opportunity to make one sample for several tests, for several tests, even in one at one parameters, to obtain some distribution. So for methods, we used such measurements as electrical conductivity, DC. For pure resistive properties, we applied custom setup to measure the temperature and current through the sample, and mostly the mechanical properties were obtained from Shimadzu tensile machine in two methods, in two ways: the tensile strength and 3-point bending. So from our general results, when we decided the concentrations, we were, as I mentioned, we were using two types of fillers: carbon black, or CNT, sorry, carbon nanotubes, and carbon black. As you may see in volume percents, the percolation threshold, well, this curve can be explained by Abbe percolation model, and Fisset, it is percolation threshold for nanoparticles is much lower. So it was quite play to finalize the concentrations and ratios between them. but after all, we reached two concentrations for this presentation, and it was one nanotube, 1 volume percent of nanotubes, 16% of carbon black, and the same for same order for second sample. So generally, in this work will be presented results for two samples, and as you may see, the conductivity will be good enough to obtain high temperature and high heat output to welding parts. So pure-resistive heating was made on a custom setup, and for as I mentioned, for two samples at different for two samples at different voltages. At each voltage, we obtain some constant equilibrium temperature that we consequently used to our let's say calculations for welding method. As we can see, each for concentration with 2 carbon nanotubes and 18 carbon black at lower voltages, we obtain higher temperatures. For example, for 10 volts, here we are. It is approximately less than 100 Celsius degrees, and here it is much higher, more than twice higher. So, as I mentioned previously, concentration and ratio are extremely important in this way, and we have to understand the needs, because after all, it will influence dramatically on mechanical properties and fatigue. Anyway, as you can see, both concentrations, both samples could reach much higher out of the range temperatures, but still, in case of lower concentration, we checked several consequent heatings, and as you can see, after 20 volts, it means more than 150 Celsius degrees, which that is higher than melting temperature of the matrix. We can see the destruction of conductive skeleton of the composite. Actually, for 30 volts, there is no third run, because after first heating, it was damaged, completely damaged. So next one, well, yeah, about the mechanical properties. Despite higher possibility to heat at lower temperature, a sample with high concentration has much lower facility to handle the force. I would like to mention that it was a tensile, but in, let's say, shear mode, because it was an overlap joint, and it was not a butt, so it is not one axis tensile. It is quite specific. Anyway, the surface area is approximately the same for both, since we used the same cut parts, welded parts, and it was approximately 1 square centimeter for both. So technically, it can be compared. In case of fatigue and 3-point bending test, we conduct some tests, and at 3 stages. First stage, it was a deformation stroke 3 millimeters, 4 and 5. As you may see, it is after the first part of cycles that has an explanation as an effect. It reaches the equilibrium stage. and we can see for the whole results except this one. For this five tests, the conductivity or resistivity was constant. So it is a bit a problem, let's say, because it is hard to precisely evaluate in the not very deep range, evaluate the status of the weld, but still it is a sensitive and it can be attached to the force. In this case, it was oriented to the stroke, but in case of force, we can work more precisely and be more precise with sensitivity to according to electrical conductivity. The same, actually, the same is for both samples, but still for high concentration, the same stroke 5 millimeters was good enough to handle. Technically, it is a bit tough to go very deep because it sharply depends on on quality of the weld and on sticking area and amount of defects. So technically, several samples for this particular work were conducted and measured. It has been shown that electrical properties obey to percolation model, and it can be used to explain behavior of electrical conductivity via the concentrations. The most important was to reach needed temperatures for such thin samples, because usually it was needed much bigger amount of material to heat and to radiate the heat. Also, according to the infrared camera, the area, actually I can show you it here, the area, well, the area, this guy is damaged, let's say, and here is from bottom to the top. It is a result of heating. So as you can see, the heated area is quite homogeneous, and it is great to obtain a good weld and good structure. So also it can be used. It can be at some points such materials can be used as a structural health monitoring device. But this topic needs a bit more experiments and shapes, let's say. But as we can see, it can be applied. So thank you for your attention. That's all for me.
Thank you. Today, our speakers is very fast. And dear colleagues, do you have any questions for our speaker? Okay, please.
I have one question about mechanical tests, about fatigue tests. How many repeats you make?
Cycles or
so how many cycles?
Cycles. In this particular case, it was not too much, only 20 for each run. Yeah, it is not. It is well, okay. It is not a fatigue like typical, let's say. But in our case, we tried to reach the equilibrium stage equilibrium stage and effect on conductivity.
One moment.
So it was only 20, so it is not, let's say, usual fatigue test, but here we have equilibrium and...
You think that it can bear more cycles, yeah?
Well, it is there is a number of cycles that must be conducted to speak about behavior as a material, but it wasn't just a purpose right here. Here we tried to catch this influence on electrical properties.
Okay. Sorry, I missed a part of your presentation.
Oh.
What does it mean, green line and red line here?
There is no green line here.
Oh,
Blue one.
Sorry.
No, blue one is whoa.
Oh, black and red. Sorry.
It is actually, that's what I was talking about. It is resistivity influence. It is on one x scale time in seconds, so it wasn't long run, but still there is a, you see, a mechanical test catch the breakpoint, and in the same time the resistivity grows up.
Okay. Okay, it's logical. Okay. Okay. Understood. Thank you.
Okay, and I have a question because you speak a lot of about properties of your material, but what about the structure of your material? You incorporate nanoparticles, carbon nanoparticles, yes, and more interest in carbon nanotubes. Do you investigate the structure of your material? Do you investigate the anisotropy of structure, special for nanotubes, carbon nanotubes? Because your properties could be not the same in different directions because it could be anisotropy of structure for some materials you investigate.
Yeah, exactly. Talking about materials, well, there are not too much information on this slide, but fillers were manufactured. So we had a data list. In case of exceptionally nanotubes, yeah, of course, there are single walls, multi-walls, ratio between diameter and length. In our case, it was multi-walled nanotube, so it is not highly top-notch, highly conductive material, and we were more oriented on industrially possible materials that is, let's say, low cost as a nanotube, as a carbon nanotube usual prices. So we didn't make a deep investigation of particular fillers, but about the composite in general. The most important for us for this stage was to catch the geometrical parameters, because as I mentioned, for some thicknesses of films, it is important to generate this ordered structure that I mentioned before. And for example, when we tried to use for the same thickness, use the fraction that is much higher than 200 microns, it was, it was visibly worse. So previously we made a geometrical model to analytically produce understand the behavior of possible behavior of the sample, and we applied it here. And according to it, we choose the fractions, the filler amounts. So we didn't investigate it particularly, but in general, it was pipeline.
Okay. And the next question you say about application of your material. It's conventionally this material used as a smart material. It's a growth sector of investigation. And what health parameters you could monitoring using your materials? Where applications could be?
Well, yeah, firstly, it is a smart material. It was this idea was introduced in our department some years ago, and we decided to stick to it because it is promising. According to the parameters, well, on the surface, it is a resistivity. but generally it can, resistivity of mechanical application of mechanical stresses. But as well, it can be a temperature detector. For example, if it will be put in some area that has some specific ambient temperature or some parameters, it can be used as a sensor. But sensor, for example, for temperature, okay, it can be, but for some acids or aggressive liquids, polyethylene, the matrix is not the best one. So this idea can be put further for a wider range, but right now we are looking for welding and for checking structure.
Okay, thank you. Is any questions for our speaker? If no questions, thank you again.
Okay,
And
thanks.
the next speaker is Natya Barbakadze from Ivan Yavishvili, Tbilisi State University, Georgia. Vastes as precursors of tungsten carbide and tungsten carbide cobalt materials manufacturing. Please, Natya. Sorry.
Thank you very much. Thank you for this opportunity to be part of this event. So I'll try to share my screen now. Is it visible? Is it okay?
It's okay, so you can
Okay.
start your speech.
So
Please.
I'll start my presentation with title Waste as Precursors in Tungsten, Carbon, and Tungsten, Carbon, Cobalt Materials Manufacturing. So this work was implemented by the participation of above mentioned institutions. It's joint work. So the purpose of our studies is to recycle various types of solid waste and examine the process involved in obtaining the certain materials. In this work, the key focus of this research was the recycling of scrap of tungsten, which is an inexpensive metal commonly used in the production of advanced materials. According to the, due to the tungsten's diverse application, a wide range of scrap materials was available for recycling. A lot of tungsten scrap is accumulated, and according to the official reports, for example, in 2000, around 46% of United States tungsten supply was derived from scrap. So the percentage ratio of tungsten consumed from new scrap to that consumed from old scrap was estimated to be 20 to 80. In our case, tungsten carbide cobalt materials were obtained from tungsten scraps and graphite foil waste. We converted metallic tungsten containing scrap into polyperoxide tungstic acid using a relatively inexpensive processing technology. Graphene oxide and reduced graphene oxide were synthesized from graphite foil waste, GO Graflex and GO Graflex. The interaction of these products led to GO Graflex PPTA and GO Graflex PPTA cobalt acetate complexes, which were converted into reduced graphene oxide Graflex tungsten OX and reduced graphene oxide Graflex tungsten OX cobalt oxide composite through vacuum thermal exfoliation. Next slide shows the key methods used to recycle such kind of waste in the production of tungsten-containing hard alloys. As you can see, here are listed all 10 methods step by step, from starting materials to the desired products. The processing of unconditioned tungsten powders to convert them into tungsten compounds using spirals like plates and other products is most effective with relatively simple and environmentally friendly technology. This process involves obtaining of PPTA from scrap metal through a reaction with hydrogen peroxide, and unlike the other method, this process releases only oxygen, which is non-harmful for the environment. PPTA was obtained by crushing tungsten scraps, spirals, and dissolving this powder in hydrogen solution. The concentration of hydrogen peroxide solution was 30%. The optimum dissolving temperature in this case was 60 degrees Celsius. The method of dissolving tungsten in a solution of hydrogen peroxide and converting it into PPTA is often used to deposit tungsten, for example, on various surfaces to form tungsten oxides. Tungsten OC3 obtained by this method has many applications in modern technologies as a photocatalyst in water splitting, electrodes for lithium-ion batteries, photochromic films, and electrochromic displays. So previously, in our previous studies, we studied the vacuum thermal exfoliation process of GO and GO metal compound complexes. With increasing temperature, graphene oxide transforms into reduced graphene oxides. Since the functional group that exists in this case, such as carboxylic groups, carbonyl, hydroxyl, or epoxide groups of GO are partially removed, the released gases between the layers increase the pressure, so their exfoliation occurs. The transformation from graphene oxide to reduced graphene oxide in air was performed at 180 to 250 degrees Celsius. Similar processes take place during the vacuum thermal exfoliation of GO graphics obtained from graphite foil waste. The temperature range of the GO-RGO transition decreases from 120 to 170 degrees Celsius if the samples are heated in vacuum. Here you can see a typical SEM image of reduced graphene oxide sample obtained by this method, and as you can see, the exfoliation process of the layers into thinner plates are visible very well. As I have mentioned, in this work, we focused on the decomposition of GO graphics cobalt compounds complexes by the method of vacuum thermal exfoliation, which is very important for the study of tungsten carbide cobalt materials formation processes. It has been established that RGO graphics cobalt oxide composite can be obtained by heating the GO graphics cobalt nitrate complex in vacuum at 120 degrees Celsius. Let me note that the cobalt nitrate decomposition temperature is 250 degrees. Figure 2 shows the diffractogram of the reduced graphene oxide graphics cobalt oxide composite. So you can see exfoliation of GO graphics metal nitrate complexes occurs instantly. So sampling was done in steel autoclave. it has been established that nitrogen oxides and oxygen formed during the decomposition of complexes containing metal nitrates partially destroys the structure of reduced graphene oxide. For this reason, it is better to use salts of organic acids, the thermal decomposition of which creates a reducing environment in the reaction region, which is very important for the process. So, as we mentioned, the goal of the work was to obtain PPTA from metallic tungsten scrap, interact it with GeoGraflex, synthesize GeoGraflex PPTA, investigate and compare their carbonization processes. PPTA containing 19.99 atomic percent of tungsten and 80.1 atomic percent of oxygen was synthesized from tungsten scrap using the proposed method. So the obtained PPTA then was used to synthesize tungsten carbide cobalt systems. For this purpose, the composite GeoGraflex PPTA and GeoGraflex PPTA cobalt acetate were formed and their carbonization was carried out at 700 to 1000 degrees Celsius in hydrogen atmosphere. As I mentioned, reduced graphene oxide Graflex tungsten O2 composite was obtained at 600 to 700 degrees Celsius in argon atmosphere. Thus, during the carbonization of GeoGraflex PPTA and GeoGraflex PPTA cobalt acetate, the following processes have taken place. At 6 to 700 degrees Celsius, GeoGraflex PPTA transforms into reduced GeoGraflex tungsten O2 and reduced graphene oxide tungsten in hydrogen atmosphere at 600 to 700 degrees Celsius is obtained from it, as you can see by the figure 4A. So its carbonization at 1000 degrees Celsius yields to the obtaining of a mixture of tungsten C and tungsten 2C. GeoGraflex PPTA cobalt acetate transforms into reduced graphene oxide Graflex tungsten O2 cobalt O at 600 700 degrees Celsius, and its carbonization, as I have mentioned, yields to the complex carbide, which is cobalt 3, tungsten 3, and C, as it's shown in figure 5A. Previously, we used organic compounds to obtain matrix ceramics. They undergo pyrolysis during carbonization and form activated carbon, a reducing agent for metal oxides and carbonizing reagent. GOs have a 2D structure, unlike in situ form amorphous carbon. So when heating the PPTA sucrose, cobalt acetate, and APT, ammonium paratungstate sucrose, cobalt acetate systems at 170 to 600 degrees Celsius during the pyrolysis of sucrose, amorphous carbon is formed. The percentage of formed carbon in this case was 21%, which is homogeneously distributed between the components of the pre-ceramic precursor. And finally, at 1000 degrees Celsius, tungsten carbide cobalt is obtained. It's shown in figure 5B. Thus, the use of amorphous carbon as a carbidizing reagent is more promising than carbon materials with 2D dimension structure. In this case, GO and RGO, so graphene oxide and reduced graphene oxide. So main characteristics of the above mentioned processes are summarized in table 1. Here you can see the starting materials, temperature, reaction atmosphere, and the resulted products. So let's move to the conclusions. Metallic tungsten scrap and graphite foil waste were used as precursors to obtain tungsten, carbide, cobalt materials. Methods for obtaining high-purity tungsten compounds from metallic tungsten containing scraps like spirals, plates, wires, rods, powders have been developed. EDS analysis revealed that PPT comprised 99.99 atomic percent of tungsten and 80.1 atomic percent of oxygen. GO Graphics was synthesized from graphite foil waste, and tungsten containing complexes and composites were obtained based on it. The phase transformations of GeoGraphics PPTA and GeoGraphics PPTA cobalt acetate composites in vacuum and hydrogen atmosphere at 170 to 1000 degrees Celsius have been studied. It has been established that during the thermal treatment of the complexes, several intermediate phases are formed, which eventually transforms into tungsten carbides. Under similar conditions, only the tungsten carbide cobalt powder composite is obtained from the PPTA sucrose cobalt acetate and APT sucrose cobalt acetate composites. That's the use of amorphous carbon as a carbidizing reagent is more promising than carbon materials with 2D structures such as graphene oxide and reduced graphene oxide. So here is the list of some our publications of our group regarding this topic. Thank you for your attention.
Thank you for your report. And any questions for speaker? Okay. If no questions, I have one. You synthesize tungsten carbide and tungsten carbide with cobalt. As I understand, the final you synthesize the powder material. Yes, it's a particles. No, it's powder material or it's
Yes.
a compound material.
It's powder material.
Powder
The
material.
resulting product is powdered material.
Okay. And do you analyze the average particle size or particle size distribution of your material? It's micron size particles or nanoparticles you obtain finally?
Yes, it's nanosized. It's from 50 to 200 micrometers.
It's a few micrometers nanopowder. And the distribution of this powder you not investigate?
It's homogeneous.
Homogeneous.
Yes.
Okay, thank you for your speech and continue our session. The next report from Vitaly Sheremet, Donetsk Institute of Physics and Engineering, together with National Technical University of Ukraine, Igor Sikorsky, Kyiv Polytechnic Institute, and Bakul Institute for Super Hard Materials. Improvement of tool reliability and mechanical performance of tungsten carbide cobalt cemented carbides with varying cobalt content by cold isostatic pressing. Mr. Sherimet, are you present? Are you ready to present? He is absent? And maybe co-authors Gennady Akimov, Igor Andreev, Yuri Besarabets, Alexander Vasilchuk, Serhiy student, Irina Trosnikova, Petro Loboda is present. Oh, sorry, it's not. Yes. They absent all? Okay. 1 minute, we try to achieve our reporter. Okay, we can't contact with Vitaly Sheremet, and we made little changes in our program. Now will be main sponsor from worldwide famous company Netsch. It's analytical instruments for investigations, for scientific investigations. Claire Strasser, curing kinetics modeling of an anime-based epoxy resin. Please, if you're ready.
Hello.
Hello.
Hello, I am Claire. Thank you very much for the introduction. So I try to give you my screen. Yes. So I think it is working. If not, please say something. Okay. So thank you for the introduction. So in this presentation, I would like to speak about a curing reaction. And I would like to show you how to make the kinetics modeling of this curing reaction. For that, we worked on an epoxy resin. So as a resin, we had diglycidyl ether bisphenol A. And as a hardener, we had a mixture of these two diamines here. If we mixed the resin with a hardener, then we get something that is flowable with a very low viscosity. And if we wait or if we increase the temperature, then we build a three-dimensional network so that we get a structural part, something that is very stiff. This reaction is irreversible. And the reaction rate here depends on the conversion, on the temperature, and on time. And in this presentation, I would like to speak about the kinetics modeling of this reaction. First, we worked with a DSC, differential scanning calorimetry. Here you see the typical DSC curve for a curing reaction. So it was our system, our epoxy resin. So we mixed our resin and hardener. We put this mixture in an aluminum crucible. And this aluminum crucible was placed in the DSC cell. And then we increase the temperature at a controlled heating rate of 3 Kelvin per minute. Here, at minus 40 degrees, we see an endothermal step that is due to the glass transition of the monomer, because at this point, the resin is not cured yet. So it is a glass transition temperature of our fully uncured material. If we go on with the heating, we see a big exothermal step, exothermal peak that is due to the curing reaction. And here we see that we don't have only a peak minimum, but we have also a shoulder on the peak, meaning that the reaction will go with two steps. It is something that is important to note for the kinetics modeling. If we want to characterize the conversion or the degree of cure, then in DSC, we work with the partial area of this exothermal peak. If we cool down our resin, our crucible in the DSC cell, and if we perform a second heating, then we get the blue curve here. So here there are two different things that are important to see. First, we don't see any exothermal peak anymore, meaning that the reaction was completely finished before the second heating. So now the blue curve, it is a measurement on the completely cured resin. And the second important thing is the big shift of the glass transition temperature. For the monomer, it was detected at minus 40 degrees. And for the completely cured resin, it is detected at 124 degrees. So we see the very big influence of the degree of cure or the conversion on the glass transition temperature. It is something that we can display in that way. So you see here the plot of the glass transition temperature as a function of the conversion. And here the point, it comes from measurements, meaning that we measured the resin at different degree of cured, and we determined the glass transition temperature for each sample. And through this point here, we can apply, or we can make a fit that is called the Di Benedetto fit, because it comes from Mr. Di Benedetto. He determines this equation here. And we will use this equation for the kinetics analysis. Why it is so important? Because we have to imagine if we work at isothermal temperatures or at very slow heating rates, then it could happen that the glass transition temperature reach the material temperature. And in this case, we have vitrification, meaning that the material goes into a glassy state, and then the reaction rate is slowed down. It could even stop completely, because the kinetics is only diffusion controlled if my material is in a glassy state. So it is not longer chemically controlled. And of course, it has a big influence on the reaction rate, so that you have to consider vitrification to get a perfect kinetics modeling. So for the reaction kinetic, we use this equation of the reaction rate. So the reaction rate is dependent on factor K and factor F. Both are a function. So the function F, it describes our modeling. Before we saw in the DAC curve that the exothermal peak was not only a peak minimum, but also a shoulder. And we said, okay, it is probably a two-step reaction. So for the F function, we worked with also with the two-step reaction. The first one was described by a Kamal-Soror model, and the second step with a nth order model. Both models or both equations are very popular to describe a curing reaction. And for the factor K, we will distinguish if we are in a glassy state or in a rubbery state, meaning if the material has its temperature above the glass transition temperature or below. In case that the material is in a rubbery state, so above the glass transition temperature, then the factor K follows Arrhenius equation here. And if it is in a glassy state, it follows a William-Landau-Ferry equation in that way here. So we applied this kinetics or this mathematic modeling to 7 different measurements, DSC measurements. So you see here the symbol. It is a measurement that we have done. They were done at different heating rates between 0.1 Kelvin per minute, it is a purple one, and 10 Kelvin per minute, it is the red one. The very slow heating rates are very long to do, of course, but they are really required because we want to modelize also the vitrification, and vitrification takes place only at very slow heating rate or at the thermal. Okay, so we see here the symbol, it is the measurement, and the continuous line, it is the curves that were calculated with our Kinetics software. It is called Kinetics Neo software. And to get this very good accordance between measured and calculated curves, we use these kinetics parameters. So we see here the first step and the second step. The first step is described by a Kamal-Surur equation. The second step, it was nth order reaction. And for both steps, we see activation energy, pre-exponential factor, reaction order, and so on. So in that way, we can model the kinetics of the reaction and use it, for example, to make prediction for any time or temperature conditions. So we have done the kinetics modeling with differential scanning calorimetry. Now we would like to use the rotational rheometer. In a rotational rheometer, we put the sample between two parallel plates here. The bottom plate stays as remains fixed, will not move during the measurement, and we apply an oscillation here to the upper plate. This oscillation has a defined frequency and a defined strain, a defined amplitude of deformation. And we measure the answer. And we can get in that way the variation of the complex shear modulus during the curing. The complex shear modulus is related to the stiffness of the material, meaning that the higher G star, it is the formula for the complex shear modulus, the higher the G star and the higher the stiffness of our material. Actually, G star, it is a complex value, and we can decompose it into an elastic shear modulus, G prime, describing the solid-like properties of our material, and into a viscous shear modulus. It will be the imaginary part of G star. It is called G double prime also, and it describes the liquid-like properties. So here, I wanted to show you in comparison how does a measurement look like if we compare it with a DSC curve. So we see in blue our DSC curve measure at 3 Kelvin per minute. I showed only the exothermal peak. And you see the comparative measurement done with the rotational rheometer. So we see not the complex stiffness, but the complex shear viscosity, but it has the same run. It is only the complex shear stiffness divided by the angular frequency. And you see here that at the beginning of the measurement, you have a small decrease of the complex shear viscosity. It is because we increase the temperatures and that results in a softening of the material. But as soon as we have the reaction, the curing reaction, then we see a very big increase of the stiffness. And the reaction is finished as soon as we reach a plateau. So for the description of the conversion or on the reaction of the degree of cure here, for the DSC, we worked with the partial area of the peak. And for the rheology, we take usually this formula in the literature, meaning that the reaction begin is taken as a minimum of the curve. It ends when we reach a plateau, and the higher the value of the shear viscosity or of the stiffness, and the higher the conversion. So we worked at different heating rate between 0.1 Kelvin per minute. It is a pink one here, and 3 Kelvin per minute. It is a green one here. You see that we have the run that we have just described for 3 Kelvin per minute for all measurements performed at 0.5 Kelvin per minute or at higher heating rate. It is the four curves here. For the lower heating rate, we see that we have additionally an increase here in the stiffness that is reversible, because here, if we heat further our material, we go again to the level of the other curves measured with the other heating rate. That comes from the vitrification of the resin. At very low heating rate, my material transition into a glassy state, and that increase the stiffness of the material. And this increase is very big. It is almost 2 decades. Because this vitrification is reversible, if we go on with the heating, then we reach again a rubbery state, and we get the same level as for the higher heating rate. Okay. For the kinetics analysis, we worked with the curves that were measured with a high heating rate, so from 0.5 Kelvin per minute. And like for the DSC curve, we worked with the Kinetics Neo software. And you see here the symbols. It is my measurement, and the continuous line, it is the curves calculated with the Kinetics Neo software, and using this kinetics parameter here. So I wanted to show you in comparison the results of the DSC analysis and of the rheological analysis. And we see a good accordance between both methods. Sorry. If we work with rheology, we can work with a complex stiffness or complex shear viscosity. We can also work with a curve of elastic and shear moduli. So here you see the example of the heating at 3 Kelvin per minute. At the beginning of the reaction, you see that G double prime, the viscous shear modulus, is higher than G prime, meaning that the liquid-like properties of the resin dominate the solid-like properties, and for the time scale of the applied frequency, it was 1 Hertz, the resin will be able to flow. But as soon as we have the crossover between G prime and G double prime, then the flowing is not possible anymore. This crossover is related to, or is an approximation of the gel point of the resin. It was detected here at 105 degrees. If you look at the DSC peak and at the partial area of this peak, meaning that we look at the partial area up to 105 degrees, that correspond to a degree of cure at approximated gel point of 67%. So I have shown you a measurement during a heating, but we can also work in isothermal condition. So we investigated the curing at 40 degrees, 50 degrees, and 60 degrees. And here we see the curves of G prime and G double prime. So the higher the temperature and the faster the reaction. So we see that at the slope of the curves. And we see also that the crossover is switched faster for the higher temperature, of course, because the reaction is faster. We can put this result in a diagram showing here the time of gelation as a function of 1 divided by the temperature in Kelvin. So here we see our 3 points related to the results that I have just shown, and we can put a linear fit through these points, and with this linear fit, we can determine the energy of activation of the reaction up to the gel point. Here we have to be a little bit careful because, of course, only the reaction up to the gel point is described and not the complete reaction as it was the case with our DSC measurements and with our rheological measurement with the curves of the complex shear viscosity. Okay, and we see that this energy of activation of 47 kilojoule per mole accords good with the results that we had before. We were around 50 kilojoule per mole also. Okay, so as a summary, I hope I could show you that we can perform the kinetics analysis of a curing reaction, and we can use differential scanning calorimetry and also the rotational rheometry. For this kinetics modeling, we used a consecutive two-step reaction, and the model used are very are wide spread to describe the kinetic to describe curing reaction. It was a Kamal-Soro reaction and the nth order reaction. With DSC, we could also model the vitrification. And for the rheological point of view, of course, it is very nice to get a rheological curve because with the rheology, you can also determine if your material is able to flow or if the gel point is switched and if the flowing is not able anymore. So I would like to thank you very much for your attention. If you have questions, please, or you can, if you want, you can also contact me per mail here. It is my mail address.
Thank you for a very interesting report. Dear colleagues, do you have any questions for this report? You have?
Thank you very much, Claire, for an excellent demonstration of the of how to do complex tasks with the niche equipment. We are, of course, epoxy resins are more or less general case. I wanted to ask perhaps two questions. We are more interested in thermoplastics here that can be used in additive manufacturing.
Yes.
And we are interested not only in them, but in loading them with solids. So what would be the approaches? Are the approaches similar if we want to study composite systems with other thermoplastics loaded with solid particles, solid.
Yes, you can make that. You only have to be careful that if you make, for example, a DSC measurement, you will measure only the polymer, but the mass, it is the mass of the polymer and the mass of the particle. So you should calculate the true enthalpy.
I imagine that the solid part would probably to some extent influence the dynamics in general. We could at least expect that. So I think we need to consider them as a system, no?
Normally, during the DSC measurement, it is like an inert material because it doesn't react.
Okay.
So
Okay.
during the DSC measurement, you will measure the heat flow, and normally the solid particles they make nothing. You know, they don't cure or don't melt. If of course if you have a reaction of the solid particles, then it should be considered. But I would measure it with a DSC and have a look. So you will see if you have only a curing peak of if you have also melting effect.
Okay, thank you, thank you. One more question is related to the equipment itself. The models you showed, the experiment here is at more or less low temperatures, up to 200 degrees C or something like.
Yes.
Do they work at higher temperatures?
The DSC with the low temperature DSC, you can go to 750 degrees. And if you need higher temperature, you can work with our STA. So you can go even higher.
And with a viscosimeter?
With the viscosimeter, you can go to 450 degrees.
Sorry?
450 degrees.
450,
yes.
Yeah,
So
that's great.
Yeah.
That's great.
We have different we have different furnaces for the.
And if I may, one more question related to the contents of the presentation itself. Slide 12. I didn't quite catch why we put those two curves together. What do we want to establish here specifically by interposing by putting the curves one on another?
I wanted to show that the curing peak. So for the curing, you have an exothermal peak for the DSC, and for the rheological curve, you have an increase of the stiffness. And
but the main temperature doesn't seem to coincide entirely.
Thank you very much for this question. It is because for the DSC, you measure only the heat flow. So, okay, so you see the beginning of the reaction. The beginning of the reaction is when you have the onset of the curve here. But the problem of the measurement with the shear viscosity is that you don't have only influence of the curing of the on the curve, but you have also influence of the temperature on the viscosity of the material. So we have two different effects. We have the temperature that lead to a softening of the material and to a decrease of the viscosity. But you have also the curing that lead to an increase of the shear viscosity. That is why.
Yeah, so that's the offset. Yeah.
It is the offset of yes,
Thank
and
you.
but in the literature, usually we take the beginning of the reaction as a peak minimum. And I should say also that here we have really a big increase of the stiffness. We have more than 8 decades. And normally, with a rotational rheometer, we measure stiff sample with a small diameter plate and very low viscous sample with a big diameter plate. And in that case, we come from something that is very low viscous here to a material that is very stiff. And you have to measure that with one plate. And here we have also a little, as you see here that the curve is not perfect. Huh? So we have also, it is due to the measurement.
Okay, great. Very interesting. Thank you very much for
You're
the
welcome. Thank you.
Thank you again for a very interesting report. And
thank you very much.
It's a pity, but Mr. Vitaly Sheremet can't visit our conference, and I claim coffee break up to 11:30. session, and the next speech is Alexander Ruch, composite materials based on aluminum silicon nickel alloy powder with the addition of max phase. Please start.
Один момент, please. А указка де тут? Чи тут нема? Все зрозуміло. А переключати середню, да? Угу. Good day, dear colleagues. Before starting my presentation, I'd like to thank organizers for giving possibility to make this report. My presentation is devoted to elaboration of composite materials based on aluminum silicium nickel alloy powder with the addition of max phase of titanium 3 aluminum C2. Please, next. All of us well know that aluminum-based alloys are widely used in industry and public life. Therefore, there is a problem for modernizing and these alloys and elaboration on new composition alloys. Next, please. This scheme shows us the type of aluminum classification of aluminum alloys, namely casting one, deformable one, and sinterate Z. My presentation is devoted to elaboration of new type of sinterate alloys, system of aluminum silicium nickel. Sinterate aluminum alloys are produced by powder metallurgy. It is a very special alloy, and it is characterized by slowing coefficient of thermal expansion, and it was elaborated for special application in air combustion technique with contact with parts of steel. As a rule, metallic particles of these alloys fabricated by atomizing the liquid metal with a jet of natural gas, enable the production of a supersaturated solid solution. We proposed new technology for obtaining metallic powder, namely melt spinning of alloy. Sorry, return please. Melt spinning of alloys with next grinding in a planetary mill. Of course, when we started work with this alloy, we found that mechanical properties this alloy are decreasing at elevated temperature. This problem has some way of decision. For example, нижня, да? As a rule, some carbides, oxides, and borides are used for these goals. But really, the mechanical properties often are decreasing after this processing. due to non-wetting of reinforcing additives with aluminum matrix. So we propose used max phase of titan 3 aluminum C2 to enhance mechanical properties of these alloys. A couple word about max phases. Max phases are layered ternary nitride carbide with a crystalline hexagonal structure. So they were found firstly synthesized by very famous crystallographer Hans Novotny in middle of 17th. But really new interest has arisen in beginning at earlier this century. And it connected with works of Barsum, Professor Barsum from Drexel University. Max phases has properties, combined properties, metals on ceramics, low density, high thermal and electrical conductivity, high strength, low elastic modulus, and they are machinable. In our economy, this problem is studied in some institutes of National Academy of Sciences, namely your institute, Institute for Problem Materials Problem, Institute for Hard Materials, etc. We elaborated the process of sintering of this max phase. Ideologically, it is just simple mixing of elemental powders, pressure, and sintering at elevated temperature in argon, for example, atmosphere. But there is but you see that process of sintering needs elevated temperature up to 1,500 and more centigrades. It's the first problem, and the second one is connected with very narrow interval of sintering max phase. You see that enhancing of sintering temperature on 40 centigrade result in yield of max phase up to practically 1960%. Morphologically, investigation shows testifies that they possesses layered structure. So we try to synthesize new ceramic materials, namely aluminum, silicium, nickel alloys with addition of max phase titanium 3 aluminum C2. We used spark plasma sintering techniques. Scheme is shown at this part of slide. And after sintering, we conducted a structure analysis. And what is interesting moment? As you see, we use aluminum containing max phase. After sintering, X-ray structure analysis shows that aluminum atoms in max phase were changed by silicium atoms. And in our composite, practically there is titanium silicium 3 C2 max phase. By the way, silicium type of silicium based max phase has more high mechanical characteristics. Very interesting results we obtained due to electron microscopy investigation. There is a frame from max phase in the sintered alloy. Between them, there is particles of nitrate, aluminum nitrate, silicium, and aluminum. Naturally, mechanical properties were testified. Obviously, the hardness, viscous hardness, is growing with enhanced of max phase content, but flexible mechanical properties has maxima at contact of max phase about 20%, and this value is in 1.5 time more than for pure aluminum alloys. Coefficient thermal expansion shows investigation of coefficient thermal expansion show that these alloys, all of these alloys, are suitable properties for using in connection with steel parts. And finally, some conclusions. As a result of the work, a metal matrix composite based on sintered aluminum alloy with the addition of the max phase was obtained. The addition of the max phase ensured the formation of uniform microstructure and contributed to the increase the hardness and strength of the material. At the same time, the coefficient of linear thermal expansion of the composite remained at the level of steel materials, which indicates its thermal stability and compatibility when used in conjunction with steel. Thus, the created composite has high potential for use in aviation technology, especially in components operating under conditions of variable temperatures and mechanical loads. Thank you for your attention.
Thank you for your report. And now the questions. Anybody have questions for?
My questions is, sorry, Pani Alexander, my questions will be in other materials with hydride of magnesium. So this is in other materials.
We use addition of max phase, titanium, aluminum, C, for enhanced properties, desorption properties of magnesium. And the result are very perfect, promising.
I want to say what hydrogen pressure was you synthesis was max phase with hydride magnesium. What is hydrogen pressure?
Yes, about 10.
Vacuum or one?
No, it was synthesized in ball milling during the ball milling at pressure up to 500 megapascal.
Desorption hydrogen pressure.
Desorption was made in vacuum.
Oh, yes.
Yes, no, it's this problem.
So thank you very much.
Okay, any questions more? Please. Academic Robert.
Okay. Thank you for your presentation, first of all. The question is about mechanisms of interaction between max phase and aluminum alloy matrix. And if you have comment the strengthening of aluminum alloy as a result of this interaction.
The strengthening alloys really.
First, about reaction.
Mm.
What's the result of reaction? What is the mechanism of reaction between alloy and max phase? And the second one, the mechanism of strengthening as a result of this interaction.
Max phase was added for strengthening, and it is a composite material. But we think because max phases has in its structure aluminum alloys, the wettability is better than in case of using for example aluminum oxide. And the second question, we obtained in sintering process metal matrix composite, and really it, as a rule more enhanced properties.
Usually strengthening means behavior of inside
It's an interesting question and need more study about dislocation.
Okay. So you don't have information about dislocations inside?
No.
Okay, thank you very much.
It is very last obtained results.
Any more questions? Okay, I have only one question. As I understand, you firstly synthesize the max phase. Yes. After this, you milled it to obtain particles, and particles we use to enhance the properties of alloy. Yes.
Really, we at low energy regimes milled max phases. It is not nanoparticles, it is microparticles used for addition.
And continue the questions of academic Ragulia. Why 20% of max phase you have reached the maximum of flexural strength? How you can explain this effect only for 20%? It's volumetric or mass person? Mass person.
First of all, it is not so bad for practical utilization because max phase is more cheap than aluminum alloys. I think it is a question to metal matrix composite because if we have very very big concentration of max phases, we in macrostructure we didn't see frame of max phases. It was not as in form of frame, but really statistical, distributed in sintered alloy. But we need frame of max phase.
Do you compare your materials with other metal matrix composites, for example, enhanced by titanium carbide particles? It's the same effect with 20% of titanium carbide addition at maximal flexural strength.
These works are making now your director and his group, Bagluk. We together with him, we started this work in sintering of simple aluminum nickel silicium alloy by powder method. But I know that some people from his group now work with enhanced properties, working with silicon carbide, etc., aluminum oxide data. But unfortunately, I don't know about mechanical testing, this result.
Okay, thank you for your report.
Thank you one more time.
Continue our session, and the next will be Dr. Sergei Ivanchenko from Frantsevich Institute for Problems of Material Science, together with Institute for Physics and Josef Stefan Institute, Slovenia. Preparation and characterization of flexible barium titanate PVDF TRFE nanoferroic nanoferroelectric composite tapes for microelectronics, please.
Hello, dear colleagues. Do you hear me well? Do you see presentation? Can I get the pointer? Okay, thank you very much. Thank you for introduction. And I want to present you our work, which was made in a framework of the NATO Science for Peace project, RAPCOM. We did this work with our colleagues from Institute of Physics in Kyiv and Institute Joseph Stefan in Ljubljana, Slovenia. And this work is about preparation and characterization of flexible barium titanate PVDF nanoferroelectric composite tape for microelectronics, and in particular for the electrocaloric cooling devices. So what is electrocaloric effect and how it can be useful for the microelectronic application? First of all, if we have, for example, a composite which have a small polar units, which we call dipoles, and we can apply electric field to this composite, the dipoles in this body becomes oriented. Therefore, entropy will decrease and the temperature within this composite will rise. And if we remove electric field from this composite, dipoles will get back to their random state and entropy will increase and temperature decrease. This process happens adiabatically, so is no exchange with external surroundings. So how we can use this as a cooling devices, because our temperature positive and temperature negative is actually equal. We need to modify this process with a very simple solution. First of all, we have, for example, at room temperature, our composite with disoriented dipoles. We apply electric field to it, dipoles become oriented and temperature rises because entropy decreases. On this stage, we must add heat removal, for example, regular heat sink to remove the heat produced by decrease of entropy in our composite. So we obtain on this stage, after heat removal, a highly oriented dipoles in our composite, but with, for example, room temperature. After that, we remove electric field and our dipoles become disoriented again, which increase entropy and therefore decrease temperature. In this case, we obtain same composite, but the temperature is lower than in initial step. This is very important step because here is where cooling happens. Here we can apply this composite to our electric device, for example, some kind of processor, and remove heat from this device to our composite. After our device hit our composite to the initial state with disoriented dipoles. And we can begin our cycle again, creating somehow something like a heat pump that will work in cycle and remove temperature continuously. What is the challenge in our work and our design of this composite? First of all, we choose PVDF polymer known for this high dielectric constant and ceramic particles. Why we choose them? Because polymer have very high electric field. He can withstand very high electric field, higher than pure ceramics. And ceramic particles can withstand much higher polarization. And they will work in the composite in synergy, creating high polarization when high field applying, resulting in a high temperature delta that we can use in our cooling pump. But real magic happens on the interface between nanoparticles and polymer, because theoretical study actually predict then applied field, the electric field that we apply to this composite, the local fields inside composite can be in 3 or 5 times higher than the field that we applied initially. Why it happens? Because we have particles with a very high dielectric constant, and electric field lines avoid these particles. They like screened with their high dielectric constant. And the electric field lines becomes crowded. They avoid particles and they crowd in between distance between the particles in the polymer. And here is why we use barium titanate nanopowder, because it has very large surface to area volume, and PVDF, not common PVDF, but modified with copolymer terphe, which allows it to crystallize in the beta phase, which can be easily polarized. And this high field, which gave us in the spaces between particles, will polarize the polymer matrix. How we create composite in our institute, in our laboratory here? We approach this very simple with standard powder metallurgy approach. We took a regular glass jar, fill 40 volume% of it with grinding zirconium balls, zirconium oxide balls. Remaining spaces fill with our 24 nanometers nanopowder. We knew specific surface of the powder, and we also apply surfactant to it with known polymer landing area. And we calculate amount of surfactant to cover all of our particles in this jar with a single monolayer of the surfactant molecules. After a few days of slow grinding in this kind of jar, we obtain 20 mass% dispersion of barium titanate particles in dimethyl formamide. This is solvent very good for dissolving also PVDF polymer. And we did a sedimentation test, and after whole week of standing, still we lose like only 1% of mass of our dispersion, which indicates a very stable, good suspension that we can work and where particles evenly distributed. So we have our ceramics composite, and next we must prepare polymer solution. We dissolve our polymer in the same solvent, dimethyl formamide, and we calculate a ratio. After that, we mix our powder dispersion with polymer solution, and we calculate the amount ratio of polymer to ceramics to, in the end, to obtain tapes with 2%, 5%, 11%, and 20% of ceramics loadings in it. And here on this video, you can see how the process goes, how we dissolve polymer in our solvent. Here how looks the polymer solution. And here I'm adding the powder dispersion to the polymer solution. As I say, we did it in a different ratio. As you can see, the structure, the texture of this mixture is quite bulky, because the powder goes away one particle from another because of monomolecular layer of the surfactant on their surface. After that, we continue with rheology measurement with 5-hour suspension. One is a pure polymer solution, and 4 suspension with ceramic particles in a different ratio between polymer and ceramics. And this study, in short, shows us that all the liquids have a thixotropic flow character, which indicates a developed molecular network, which is promising for us because we believe that this network is able to hold even high ceramic loadings. And here on this video, you can see improvised tape casting process for a small laboratory production. Very simple, do on the glass surface. After casting the tape, we dry it immediately. And as you can see, the structure of our tape is absolutely homogeneous without any visible agglomerates, which indicates a good distribution of particles, which what we actually aiming from. Because high loadings of ceramic particles, which will be evenly distributed in the volume of the composite, will give us more areas where the charge can be amplified because of crowding of electric fields in it. We also did some modeling of particle distribution, which showed us that even with high ceramic loadings of 20 volume%, we still do not reach a percolation threshold in this composite if everything will go good in this situation. Also, we perform surface roughness with optical profilometry. We check thickness of the tape. Tape thickness was around 5-6 micrometers, and surface roughness was about 50 nanometers, which can be compared to the well-polished steel, for example. And interesting last stage of this process, we remove from the substrate our tapes. We did it underwater because interface water helps removing the tapes from the carrier, glass carrier, because it flows into interface between them. And so we can remove these tapes without destruction, without stretching. And in the end, we obtain this very good looking composite tapes. We perform next a Fourier transform infrared spectroscopy to check if we obtain this beta phase, which is very important for us in our composite because it's, I remind you, is a crystalline phase of the PVDF polymer, which can be easily polarized. And we obtain a few significant bands here, which indicate presence of beta phase. But also interesting here, as you can see on the edge of sensitivity of our device, the composites with the ceramic particles, they also have additional band of the beta composites, which pure polymer film without particles do not have. It can mean that ceramic particles work as a nuclei for the growth of the crystalline PVDF polymer in this case. And after that, we transfer our particles to the Institute of Physics. They perform dielectric constant measure, which was 64 dielectric storage permittivity units with very low dielectric losses at 1 kilohertz at 70 degrees Celsius. And then we send our samples to the Slovenia, to Josef Stefan Institute, which perform research in electrocaloric response of this film. And the result was quite promising because, as you can see here on this graph, our 20% volume load of barium titanate gave us 22 kelvins electrocaloric effect, which is quite high and almost 2 times higher than pure polymer film without addition of the powder. That means that we achieve stable interface, a stable particles distribution, even distribution in this case, which gave us quite high results. But we do not stop on this. We have some ideas. The project is still going on. It's only like a second milestone of the project. And we have another ideas how to make it even better. But for now, we have 5 micron films that gave us 24 Kelvin electrocaloric response from it. Our previous research in this project were published in 3 publications of Q1 quartile. And if you want to follow our research, if you're interested, you can check this out. And I thank you for your attention, and I'll be glad to answer your questions.
Thank you for your report. Any questions? Please, Julio.
Thank you very much, Dr. Ivanchenko, for your talk. Interesting results, of course, very perspective. I have a question about measurement of dielectric constant. So you showed the shift of Curie point to the lower temperatures compared to pure barium titanate. How can you comment this shift? Is a size effect?
And the shift, can you please give me control? Yeah.
This one.
Here, you mean this shift?
Yeah, I mean, yeah, that's almost 70 degrees, but usually the Curie point is near 120.
Yeah, I believe this is a side effect because we work not with pure material like barium titanate. We work with nanoparticles first of all, and with polymer. So we work with
what is the Curie point for PVDF and terphenol?
For PVDF, it's around. It's closer to the 70 degrees. I believe it's like 80, maybe.
So this is mostly dielectric behavior of polymer rather than nanoparticles.
Yeah.
Okay.
But still, the composite, the shift of the particles, like 120, shift of Curie temperature is also observed for the whole polymer. So we do not have at this temperature nothing on this stage. And of course, the main role in this composite plays the polymer. It will be polarized, and the particles plays as a supportive roles to better polarize polymer matrix. So it's not a surprise that we have this shift in this area closer to the temperature of the polymer Curie shift.
Okay, you demonstrated you can orient or alignment of particles inside the electric field. So can you show the difference in the measurement of epsilon for ordered and disordered dipoles of both polymers and particles?
Actually, I do not have it on this slide because all these measurements were conducted with applied electric field, and they ordered in some way on all of the graphs. Because without applying a field,
Interesting. Have you measured indeed in the field?
we need the electric field to perform measurements.
You apply the electric field when you measure the electric properties.
Yes, and we can't measure without field. So we can't measure with disoriented structure.
Okay, this probably an explanation of quite high ton delta for your material.
All this measurement is with applied field because there's no other way to measure it without field.
Okay,
at least I don't know, but it is in you touch an interesting topic to compare these states. Thank you.
Okay.
Is there any more questions, please?
Well, yeah, thanks for your presentation. I have several questions. Firstly, you introduced your topic and you presented it as a possible application. So I would like to ask you, did you, let's say, calculated the effectiveness of such device, and how effective it will be to apply the field different temperatures? So this how have you measured it somehow?
Yes, it's currently, this is the last measurements that did our colleagues and the Josef Stefan Institute. It's not completed yet, but they have already have some results, but I can't share it. It's still in the process, but we, of course, it will not be as high as this clean clean effect that they calculated from the film. Of course, there will be jaw heating in this device, and a massive heat conductors will be applied also. No, any heat conductor will be massive compared to the 5-micron films, for example. So the performance of device in assembly will be lower, of course, than this clear data. But we can apply the beauty of this process, because we can apply it in a cycle. So even a low change of temperature can be used in the ready devices.
Like delta. And next question about sample preparation. Terephthalate, it is a hydrophobic material, but how you dry it with temperature in oven, or how it was, and how it influenced on properties of your sample?
It's very good question, because we have some problems with it actually when prepared such kind of materials. We have dimethylformamide solvent with a high evaporation temperature, and we need to find balance between allowing polymer to find its structure and heat it up to crystallize polymer to trap particles. So if we let it sit for a long time, the particles tend to agglomerate inside, and we do not want it. And if we do not let it sit for a long time, that will be a decrease in beta phase formation. So polymer wants to sit freely and form these long molecules and structures, and the particles, they need to be heated just after casting to be trapped in the homogeneous way in the structure of the polymer. So this is like a balance we took.
Yeah, it is tough at temperature, and find the balance temperature.
Yeah, the heating temperature, if you are asking this, was 60 degrees Celsius, and we also apply a heat exchanger on a hot plate to evenly distribute temperature to avoid regions with higher.
On the video.
Yeah, yeah.
And about the particles, the surfaces are modified, but the sedimentation can appears. How do you fight this effect? Well, it is quite tough as well.
No, first of all, we, as you can say, we modified surface with a surfactant. So we have negative charge on the surface, and other particle will also have this monomolecular layer, and they will reflect each other. And that's basically all. It's electrostatic stabilization from colloidal chemistry.
I mean, during operations, there is still some volume, and nanoparticles will sedimentate, go down.
Yeah, they will.
So it's not about interaction.
But do not forget about PVDF polymer solution. It's have a quite high viscosity and developed matrix, which showed us rheological studies that molecules are entangled without each other. It's like a network of molecules, and a very high, not very high, quite high viscosity that can stabilize the particles plus their electrostatic repulsion. And all of that, if we heat it quickly after casting, you see this almost like a mirror surface on this composite without any.
I'm sure it is 5 microns because it's really a thin film.
Of course, yes.
And the very last question, sorry, about the electrical permittivity measurements. Firstly, I didn't get why you didn't make the raw material without dipole orientation.
Because to measure all this dielectric permittivity and the electrocaloric effect, we need to apply some kind of field.
In the cell, you mean? In the cell. measurements?
Yes, yeah, of course. We
Not
like
high enough to completely, let's say, no?
to see any changes.
Yeah, yeah.
We must apply a field. In its lower field in the dielectric storages, it's as you can see, the measure of field is quite high field here. Because without this field, there will be no experiment, no measurements. That's all.
Okay. And about the apparatus in Institute of Applied Physics, what is manufacturer of that apparatus?
I don't know, but I can tell you about our apparatus that we also have. We developed our own in this time, and not, I mean, measurement procedure, not the apparatus. We have Nova control.
Nova control.
Nova control, yeah. And I don't know about Institute of Physics. Didn't ask them, but I can if you're interested.
Just interested. Okay, thanks.
Impedance spectrometer, Nova control.
Vladislav Billy, please.
One last short question. Did you investigate dependence between grain size and this electrocaloric response?
We do not, in this particular study, we do not investigate that, but we have some composites with a micropowder. But the main idea behind design of these composites to have small particles to enlarge ratio of
this beta
surface. So ideal will be to have all the polymer filled with particles that will not touch each other. So they will homogeneously will be distributed. And the large particles will give us like big gaps between them. And smaller particles give us smaller distance between them. Yeah. And in this small distance, we'll crowd our electric fields, increasing polarization. This is the main concept behind this.
Okay, yeah. Thank you very much.
Thank you for the question.
Thank you. And if possible, a brief question. Barium titanate is well-known dielectric material, yes, and it's known for long years. And it's present novel dielectric materials which have better dielectric properties and which is perspective for your investigation in future.
Yes, I believe it is. It's actually not my topic of the research, but I believe some with plumbum, barium plumbum. Yeah, but not only the like chemistry of the composite, but form. We plan to work with rods, barium titanite rods, also modified with different additional composites, but it's not present in this work, but we have planned for this.
It means that barium titanate is a better today material, dielectric material, yes? Or
it's like a well-known, easy to get, and because its chemistry is well-known, it's easy to operate with it.
Okay, thank you.
It's handy.
Thank you very much.
Thank you. Thank you.
Continue our session. The next speaker, Pavlo Barvitsky. The effect of silicon carbide powders with different dispersity and morphology on the densification and mechanical properties of hafnium diboride based on ultra high temperature ceramics. Pavlo Barvitsky is present. Pavlo Barvitsky, if you're present, please make a sound. All present Tatiana Prikhna, Anastasia Lokatkina, Viktor Moschil, Leonid Devin, Sergey Ryachev, Victoria Belarusets to present results. Okay. Okay, waiting a few minutes for Pavlo Borovitsky. Okay, Pavlo Borovitsky is present. Could you start your presentation, please?
I must start this on my computer or in your...
Please start your presentation for your computer.
Видно?
Yes, we see.
Yes, we see.
But not on full screen. Please press Control L to make it full screen. Oh, thank you.
Good afternoon, colleagues. The development of ceramic composites with superior physico-mechanical properties for operation under extreme oxidative and high temperature conditions remains a major challenge in modern material science. Progress in this area depends on designing materials that can resist ablation, corrosion, thermal shock, and radiation while still being cost-effective and relatively simple to produce. Refractory ceramics based on borides, carbides, and silicides demonstrate high oxidation and corrosion resistance, even at ultra-high temperature materials. That makes them excellent candidates for aerospace applications such as nozzles, nose cones, and leading edges of hypersonic vehicles. In this, well known that silicon-contained additives can significantly improve hardness, fracture toughness, and oxidation resistance of borate-based ceramics. In our previous studies, we found that the ablation of silicon carbides together with optimized hot pressing parameters significantly change the mechanical properties of boron and boron-based ceramics. In this work, we prepared hafnium boride-based composites by hot pressing under pressure at 25-30 megapascals. True structural types of SITSE powders were used, 6H and beta modification, which differ in grain size, impurity content, and particles morphology. The morphology and chemical composition of these powders were characterized by SEM and ADX analysis. In this work, we used 4 different types of silicon carbide powders. In fact, about 12 were examined in our work total, but only on these 4 types we studied in detail full. Why we used silicon carbide as a modification addition for our composites. The silicon carbide additive during sintering silicon carbide particles in interfacial reaction forming small amounts of liquid or amorphous phases that facilitate diffusion and promote densification. This lowers the sintering temperature and increases the composite density. Since silicon carbide inhibits the grain ground of hafnium boride during sintering, leading to a fine grain and uniform microstructure. This results in more homogeneous stress distribution and improves fracture toughness. Silicon carbide improved mechanical properties due to the highest hardness of silicon carbide that the composites significantly higher hardness, weaker hardness, young modulus, and flexural strength and bending strength. Silicon carbide forms the protective CO layers on the surface when exposed to oxidation environments and high temperature, which prevents further oxidation of hafnium boride. And it's forming it creates to formation the solid solution in our composites. The silicon carbides also reduce the sintering time and temperature and proportionally decrease the amount of hafnium diboride powder required, which is extremely expensive while not degrading but rather improving to the overall properties of the composites. The best development composites from hafnium boride with 38% beta silicon carbide, 510 nanometers microns by hot press and 30 megapascals exhibited weakest microhardness, 38 and 6 gigapascals, and fracture toughness 7.7 megapascals. The best mechanical performance in terms of hardness on young models was achieved using large fragment like silicon carbide grains 30 50 and compose some degree of solid solutions using visual diffusion of element during singe. Also, no string correlation was established between the chemical of the resulting phases. It was observed that the high hardness and young models occurred in composites where the post-sintering phases contains minimum oxygen and were fabricated from powders with commodity silicon carbide.
It's a problems with light and electricity today, and some of our speakers have. Pablo is here. Could you you can continue your presentation, or it's finished?
It's finished.
It's finished. Okay. Thank you for your presentation. It will be quite better that it will be not a poster and PowerPoint presentation, because it's quite small text and it's hardly to estimate the your investigations, but I think some of our participants have questions for you. Please.
Thank you very much for your presentations. I a little bit know about the work of your group where you stay with Tatiana Prichna, and I want to ask you about what is the optimal amount of additive silicon carbide in your case? Because you didn't say about volume percent or mass percent of silicon carbide which you added to hafnium diboride.
We work with from 10 to 60% mass percents of silicon carbide in our composites, and now we stopped at 30% because these composites have much young models and fracture toughness with low density. If we used more silicon carbide powders in our composites, mechanical properties significantly are lower, and the temperature the ablation test and temperature of start of melting is lower.
I see. What do you think about for such optimal amount of silicon carbide will be also the same for other element of this group, such titanium or zirconium? You try, or you know maybe literature data of this? I mean, you use
As addition as materials of this group.
yes.
Yes,
I
we
mean,
work.
silicon carbide you can put in titanium diboride or zirconium diboride, and this 20% will be optimal for other element. These questions. What do you think?
We work with other patterns and other additions such as zirconium diboride, zirconium carbide, titanium diboride, titanium carbide, and boron carbide. Now we work with such as hafnium diboride is very
I understand. You didn't try to put such composition for other diborides of this group.
yes, but now we stopped with silicon carbide because we see approximate line what we how much powder how powder we additive use as additive and what properties we have. In case when we use other from this type of materials, titanium carbide, titanium boride, or zirconium boride, we in finished have solid solid phases and solid solutions, and in this case the temperature of the highest temperature of 10 gradus.
Degrees.
Degrees, 10 degrees or lower than 10 degrees, we have in finished another material.
Okay, and I have one last question. You said about you investigated ablation of such materials. Did you investigate the mechanical properties after ablation or no?
Yes, we have discovered mechanical properties of materials after ablation test. It's another side of the bulk зразок.
Sample.
Sample, yes. Bull sample, but on the aim of the ablation, we can't it discovered, or that's why we have some mechanical tests on these materials.
Okay, thank you very much.
Thank you.
Thank you. Tonight, the Russian aggression against Ukraine continued, and now we have some transport collapse, and some of our participants, our lecturers can't reach the institute or connect to our session. It means that Dr. Tatiana Solntseva can't reach the institute, and I claim the lunch and waiting for you at 2:00. It will be keynote of Professor Salvatore Grasso. Thank you. Yeah. Dear participants, we continue our session. And now the keynote speaker, Professor Salvatore Grasso, with a report about energy efficient ceramic processing from ultra low temperature cold sintering to ultra fast high temperature consolidation. Please, Professor Grasso.
Yes, good afternoon, everyone. My name is Toto Grasso. So first of all, I would like to thank the organizer for the big effort and also the kind invitation. And today I will be talking about new firing techniques that have the potential to reduce the carbon footprint. So in particular, we are interested in, oh, sorry, the screen disappeared. There goes, there we are. So we are interested in new firing techniques that are either proceeding at ultra low temperature. So we are looking at cold sintering type of approach, or we consider ultra short firing techniques. So you can think about maybe a very fast cook piece of meat in a very short period of time. Or if you want to make an analogy with the food, something which is cooked at a very low temperature, but for a long period of time. But the main reason to choose between these two approaches is essentially to save energy. So this work has been made possible thanks to international collaboration. So we have been collaborated with within my university, Queen Mary University of London, Southwest Jiadong University in China, Guangdong University of Technology again in China, and the University of Trento. So the full list of contributors are in the papers, so the list was too long to be included here. So I thank all the contributors and also the research founders to enable us to carry out this work. So let me introduce the outline. So here we introduce the decarbonization challenge. So how we are going to reduce emission associated with the firing. And we look at the paradox of either using cold sintering or an ultra-fast firing. I will give you an example of how much energy we can potentially save by employing these type of techniques. Then I give you some example on the cold sintering approach. Then I will touch on our new development on ultra-fast firing, and I will try to anticipate the future trends by looking at hybridized sintering. So hybridized sintering is a combination of sintering technique in order to achieve a target property or microstructure while still reducing the energy consumption. So if we want to reduce the firing energy when processing ceramics, we need to look at each single steps. And clearly, one of the most demanding and energy consuming step is the firing, which on its own account for 55 to 80% of the consumed energy. This is clearly materials dependent. It means that for some materials, we might require a lot of energy for the purification step, or maybe for other materials like natural graphite, it is already available with acceptable level of purity, but this resource might be scarce, and so each material has its own essentially status for the energy requirement. So this is a good graph which somehow suggests how we can potentially save energy or decarbonize the sector. So we are looking at the heat management and heat recovery, use of new firing techniques, but also look at the fuels. So there is a lot of talking at the moment in terms of using hydrogen for firing the ceramics. There have been some attempts all over the world, and we see some very promising results. So what I would say, though, essentially we are working on a review which summarize a different attempt to save energy. And what we realized when we tried to write this review paper is essentially that cement is well ahead of the ceramic industry. It means that for making green cements, the embodied energy is in the order of 4 megajoule kilogram. So if you want to fire an alumina at same temperature, the embodied energy is 14. So there is a clear difference of about 10 megajoule a kilogram. This is mostly because cement industry is mature. If we want to put in numbers this challenge, the ceramic market is huge, especially in volumes when we look at traditional ceramics. And overall, they contribute to 1.5% of the global energy use. So there is a strong need to develop novel firing techniques. So I'm not able to go into the details, but if you just think about the emissivity of the material used within the furnace, this is very important. So for example, inside the furnace, we want to have a material with very high emissivity to reflect the radiation and homogenize temperature. On the shell of the furnace, we want to have a material with very low emissivity in order to minimize the heat losses by radiation on the outer shell of the kiln. So this is a sector that has been towards modernization over the past 2 decades, but there is still a lot of work to be done. So sorry for the notice here, but we want to publish our own papers, and I'm aware that this will be online. But essentially, this is a mapping of the different type of materials and their emission. So as you can see here, if we consider the big emitters are essentially the cement and the concrete industry, that may account for in excess of the 20% of the global CO2 emissions. So these are the big challenge for us to be addressed. If we look at the ceramics, we have big issues associated with bricks and glasses for windows. So these are big emitters. If we look at engineered ceramics, the emission, except for alumina and maybe silicon carbide, are very small. So it's a very small fraction of the emission. But said so, this emission might become quite significant when we have batch processing or some functional ceramics. So we have very well diversified numbers of say materials for battery or for ferroelectrics and so on. But this requires a very high embodied energy per unit of mass. So clearly what we want to do is to develop novel firing techniques where essentially we are able to satisfy the drop in pollution, so CO2 associated per unit of mass. One approach to do so essentially is to use bio-inspired type of techniques. So we are looking at cold sintering, or we are looking at ultra-fast high-temperature sintering. So these cold sintering techniques typically work at a temperature below 300 or 400 degrees. Now, bear in mind that this is the temperature of processing. But when we look at sintering, we should bear in mind the temperature relative to the melting point. So if a compound has a melting point of 200 degrees Celsius and it's at room temperature, then it's likely that this material may be possible to be cold sintered at room temperature without any heating. So it's relative to the melting point. And so when we look at cold sintering, there is a very strong multidisciplinary approach because we combine together biology, geology, physics, and chemistry. And this sector is well in development. Now, if we look at the natural rocks, we can have mountain, right, made out of sediments, and these are huge, right, a kilometer in scale. In the lab, we are not able to reproduce what nature does in terms of scaling up. The main reason why we're not able to produce ceramic effectively using cold sintering, to my point of view, is essentially we are trying to rush up the process. So it means we want to make sediments, compaction, lithification, maybe in a time scale of few hours, while nature may take tens of years, if not centuries, to produce these rocks. So this process itself is very gentle in terms of amount of energy transferred to the material, and the heat might be minimal or there is no heating at all. So the main question of this cold sintering to effectively be applied might be first identify the materials that are compatible with the technique, then identify the solvent, and then understand the process and the mechanisms behind it. At the moment, our understanding of the process is rather limited. There are some very good effort, but more research work is required in order to make these techniques as a viable manufacturing techniques. So on the opposite trend, so the very short time but very extreme heat is another option for ultra fast firing. Now, in terms of fast firing techniques, the upper limit of temperature is essentially dictated by plasma. So there have been quite a few work using plasma for heating and sintering. And so if you might be familiar with arc melting, so when we go to this very extreme high temperature, and we work with the very strong temperature gradients. So the temperature is a very dynamic concept. And so we are not able to perfectly quantify what is the temperature of our sample, but we have a temperature distribution within our material essentially. So these are the general approach. So we want to look at energy efficient manufacturing. So the energy is minimal, but also we want to have processing time as short as possible in order to maximize the processing throughput. So here there are some nice examples of cold sintered material. And cold sintering in dry conditions, so it means dry press essentially using uniaxial pressing. And we have further here graphite, we have boron nitride. So these van der Waals layered materials can be cold sintered at room temperature. And this is to do with the slipping between the flakes. And I will tell you more details about this. When we look at the ultra short time, we need to develop better setup in order to effectively save energy. So these techniques scale up with the size. What does it mean? If we make small samples, say like in the case of flash sintering, the weight of one sample might be half gram, we are not able to effectively achieve energy saving because we have massive losses by radiation, but also because the ratio of the radiative surface to the volume is not in favor. So if we want to achieve low manufacturing energy, we need to develop novel setups. So I will introduce this powder-based ultra-fast high temperature sintering. So let's look at some case about the cold sintering. So cold sintering is a very exciting work, and there are few approaches. There is a cold sintering standard process, which is dry, and essentially this works well with ductile powders. Now the question is what ductile means. It means that at the temperature we press, then we achieve sufficient deformation to fill up the pores and so remove the empty space. So this works well with a large numbers of compounds. But when we have a dry press, we may also have a situation where we can compact, we can fragment the particles, we can remove the pores, but then there is no adhesion between the particles. So the material is 100% dense, but it has no strength whatsoever. So in order to avoid that kind of scenario, there is a cold sintering process where instead there is a presence of an additional solvent. The headache comes in how to choose the solvent. People have good understanding maybe about the eutectic and the dissolution of the particles and the solubilization and so on. But then we don't really have a good understanding on the interaction of solvent with the particles in order to target a certain compounds, a certain phase at the grain boundary, in order to both achieve densification, but also target a certain properties. There are different type of techniques analogous to this. These are in a seal environment, so the hydrothermal hot press. So the hydrothermal hot press was developed in the 60s. The cold sintering process was developed about 10 years ago. The difference between the two is this hydrothermal hot press is sealed, while the cold sintering process has a gap between the punch and the die, and so the solvent can dry up during the processing. So we analyzed the different type of techniques. The drive to develop this cold sintering type of process has been mostly linked with bioinspiration. So try to replicate nature. So you can think about the human tooth, and you can think about lithification, so stones. And the other additional advantage of working at room temperature is that not having heating, we can work with radioactive materials. So there's been a lot of work on nuclear waste encapsulation, and so having the ability to work at room temperature, it also become possible to integrate together organic and inorganic materials. So for example, polymers and metals, and this would not be directly possible using other techniques. And this cold sintering work, hydrothermal sintering work, has been going up and down. So here I cite the sentence from 1964. We did some work using this hydrothermal sintering. So essentially they were using a vapor for sticking particles together. But then they said, we do not intend to continue this work because there is no interest. We don't find any possible application for this type of work. And since the 2015, with the work from Professor Randall, there's been a very strong interest on cold sintering process, mostly because of the low cost, the simplicity, the versatility, but also the environmental aspect associated with the process. So I believe now we have a few hundreds of papers published every year on the topic. So we did some work, and our initial understanding showed that essentially we have a very small amount of liquid when we press particles together, and this small amount of liquid may have a dynamic effect. Then the other, when we look at isostatic pressing condition, when this process of dissolution is exothermic, when we increase the applied pressure shown here, then we increase the dissolution rate. So this will happen in isostatic condition. And the other important things to mention about this approach is that it's very extremely gentle and use a very small amount of energy, so almost no heating. So this is a nice representative picture where we have two single crystals of sodium chloride and we wanted to join them. So these are the single crystal. To join them, what we did was to use a humidity control. So we put the two single crystals one on top of the other. We did not use any solvent apart from the humidity. So we increase the humidity in the chamber, we hold for a certain period of time, and then we let it dry again. And then we try to look at the interface. So there is no interface visible. So the joint is ideal. There is no defect at the interface. So this to show that if you're trying to join this sodium chloride single crystal together using thermal-assisted processing, it might be very, very difficult. These two single crystals will not join. But if you just put it in this environmental chamber, then we're able to achieve a good joint. So we did also some work on the joining of quartz, and depending on the surface roughness and depending on the condition, we able to achieve a strong bond at room temperature. Clearly, since the dissolution of the interface is affected by the processing parameters, so the loading of sodium hydroxide, the applied pressure, the drying condition, then we get a drop for a rough surface. The interesting thing, though, is that these materials are joined at room temperature, but they maintain the strength at high temperature up to 1000 degrees. So there is a lot of interest in developing joint without any thermal affected zone. So there is no heating, there is no distortion, there is no surface damage or structural damage to the materials we want to join. This technique is also versatile and can be adapted for sintering silica. So what did we do? We make a slurry with silica and sodium hydroxide. We put in rubber dies. We do the cold isostatic pressing, and then we allow for a very slow drying process. And some of the samples show very high inline transmittance, so essentially they are comparable to a glass. And clearly, if you compare these materials in terms of hardness and processing temperature, they stand out in their own spot. Now we look at the material that is very good to be processed with cold sintering, which is graphite. So as you know, graphite is a layer structure, and we apply the pressure. The flakes orient in the direction where with the z-axis parallel to the pressure. So we achieve a highly textured materials, and depending on the pressure, the graphite flakes, then we can achieve nearly fully dense materials. So for example, with 300 micron flakes, we achieve density in excess of 99%. So the mechanism of bonding is essentially involves slipping of the flakes, and also there is a formation of van der Waals bond between those flakes. This process essentially gives a material that is similar to highly ordered pyrolytic graphite. So we did also some magnetic measurement, and we see the levitation of this cold pressed graphite. And the other interesting aspect of this type of research is that when we cold press the graphite, we form a van der Waals bond between the flakes, and this bond is reversible, which essentially means we can fragment, recompact as many times as we want. So somehow this material is recyclable. We did the same things with other van der Waals materials, and depending on the pressure and the type of flakes, the level of crystallinity, we achieve a different degree of densification. And mostly the mechanism of densification are slipping between the planes. So we did some analysis about these works. The surprising things we found out is that this cold-pressed graphite has thermal conductivity orthogonal to the Z-axis in the order of 600 watt-meter Kelvin. So the upper limit, theoretical limit for this material, for the HOPG, so the single crystal graphite, will be in the order of 2000. So clearly having larger flakes and having highly oriented materials help to achieve ultra high thermal conductivity for this cold pressed graphite. And as I mentioned to you, this works well for uniaxial pressing. So we did uniaxial press and machining, but likewise for isostatic pressing. So we can achieve caps or other type of shapes we are interested in. Now I'm going to give you an overview about the ultra-fast firing works. And as you're well aware, since the 90s with spark plasma sintering, there have been a few different types of electric current assisted sintering technique. The concept more or less is always the same, is to use jaw heating on the sample or nearby the sample, and this is to allow ultra fast firing but also low energy consumption. And there are some good advantage of doing this fast firing type of process. It's because we can refine the microstructure depending on the activation energy of densification over grain growth. So these work very well in the case of alumina. But also there are conditions maybe where we sinter the material like silicon carbide at temperature that are well above the standard processing temperature. So maybe temperature for the silicon carbide in the order of 2300 degrees, but for a short period of time. And this strategy works also for material that are not strongly thermodynamically stable during the processing. So we are looking here at the solid state electrolyte. So as you can see here, this electrolyte has a good bond with cathode or with the testing substrate, can make half cell, and this is because essentially there is a minimal loss of lithium during the processing. And we did some work on trying to achieve ultra short sintering time, and we then took a quite challenging material to be processed. And so we tried to produce dense silicon carbide, boron carbide, 50-50 composite with a very short period of time. So it's possible to densify this material in 3 seconds as long as you achieve a liquid phase. I suppose we haven't got evidence, but it's likely that the boron carbide approached the melting point, and so we get this very nearly instantaneous densification. Of course, when we will do this approach using arc plasma, so essentially we run 3 welders at the same time, we achieve a very hot spot, but likewise we achieve rapid losses. So in order to minimize losses, we need to thermally insulate the heated zone. So what did we do was to thermally insulate, for example, the flash sintering or the arc plasma, any kind of process you have in mind. And so we can achieve energy consumption in the order of 5 to 10 megajoule a kilogram. So this might be half of the conventional sintering process. The main issue is that when we do this using the flash sintering, our sample are too small and do not have a practical application. So we are limited to this shape. It's very hard to work with different type of shapes using the flash sintering. So in order to address the issue of shapes, size, we are looking at a new type of technique. And this type of technique is graphite bed powder base ultra-fast high temperature sintering. So I'm aware of some research done in Ukraine about graphitization using graphite powder bed. Is somehow similar to an Anchison furnace, if you wish. And clearly this addressed the issue associated with the felt. So if you try to sinter a sample using the felt, we have an issue of the edge. So we have very poor homogeneity, we have cracking. But if we instead we use a graphite powder bed, we can make complex shape. As I will show you, we can make components in the order of few hundred grams with the furnace we have already developed. So this was the initial generation. So this was essentially a graphite powder bed box with 2 electrodes. We have the sample in the middle, and we achieved dense material. This was well suitable for sample in the order of 10 millimeter. Then this was improved with the second and the third generation type of machine, where we have the electrode top down. The top-down electrode helps with the temperature homogeneity. As you can see here, when we have left and right side electrode, we have asymmetry top and bottom, and this results in minor heterogeneity within the sample. But when we have a top and bottom control, we have a better symmetry, and so we also have a better temperature measurement point. So this is how the setup looks like. So you can do the UHS using graphite paper. And this is good for lab testing, works with very thin samples. And the main advantage is the reduced carbon contamination, I would say, compared to the felt. So with the felt, we can go slightly bigger, but with this powder UHS, our sample can be up to 5 or 6 centimeters in diameters. I will show you in the next few slides. The other big challenge we have in this type of technique, since the temperature rapidly changes, a bit like when you switch on a light bulb, it's very hard to measure the temperature. So assuming that our power stabilizes around certain set values, then the temperature saturates, so we can correlate powers respect to melting point of materials. And the other issue we have in these type of techniques is that if we open a window for observing the temperature, then we tend to underestimate the temperature on its own. This is because there are very strong heat losses. So this powder bed is very well thermally insulated, right? So it doesn't lose heat, but the moment we open a window, then we have an issue of ability to record accurately the temperature. This is one of the main challenge. So these are the four sintering parts for the silicon carbide. And interestingly, there was a different chemistry depending on whether we heat up slow, fast, we compare with the conventional sintering, and so on. So when we have these for a very fast heating, so 1500 degrees per minute, then we tend to stabilize the 4H polytype of the silicon carbide. And this is mostly to do to the transient chemistry. So what we realize is some of the elements that were essentially surviving when were heated very high temperature, and so they affect the type of silicon carbide retained in the final sintered parts. And more recently, so this year, we got these papers on Scripta, and essentially we did a more detailed analysis on the impact of the heating rate. So we did work with alumina sample 5 centimeters, silicon carbide sample 5 centimeter. And as you can see, we're able to achieve from grain, we can able to achieve sintered part, but also crack free. As you well would imagine, the alumina has a lower thermal conductivity, so most of the heat is dissipated on the graphite powder bed and then is transferred to the sintering parts. So clearly there is a densification that happen over the time during the heating process, but then we don't have much jaw heating within the sintered material, so it's not like the case of SPS. And depending on the condition, again, we struggle to measure the temperature. We run the test, we rest some elements like silver, copper, nickel on top of the sample. We interrupt the sintering run and we see whether it's melt or not. And then we confirm the temperature and we calibrate temperature using this kind of approach. Of course, if the process is run too fast, we get a very strong thermal gradient. So this is the case, assume of 500 degrees per minute. And then we get a cracking and we get heterogeneous densification. This is because the shell here sinter first, and this then cause gradient and stresses. And this is an issue that we need to bear in mind. And so we did the work depending on heating rates and different kind of condition. And clearly the silicon carbide could be even processed at 1000 degrees per minute, and we did not observe cracking. But in the case of aluminum, we did observe cracking even at heating rate in the order of 500 degrees per minute. And so we look at the temperature distribution, the correlation between holding time and the relative density structure of the materials. And what we realize that there is a very strong significance on the temperature homogeneity. So if during the process our temperature distribution and its homogeneity is asymmetric, then we get issue with the cracking, distortion, and poor quality of the sintered materials. So if we carry out the process carefully, both in the case of silicon carbide and alumina, it's possible to achieve a fairly uniform distribution for the hardness, which match the grain size distribution. So these are data point of hardness taken at different location. So those are well acceptable, or they will be also comparable to other type of standard sintering techniques. Another more interested and unusual type of work that we have done is sintering under heat pulses. So this sintering under heat pulses essentially means that we increase and decrease the power. So the red curve is the temperature. So in this case, we are trying to sinter zirconia. And what we do, instead of having a flat profile, as you would do normally for sintering, we allow for the temperature to go up and down, up and down. Of course, this becomes very quickly very complicated. So we limited the number to 3 and 5 pulses. But on average, the processing temperature is well below the standard sintering temperature. Now, if we do this analysis depending on the number of pulses, we are essentially able to achieve a final microstructure within the materials. This is mostly because we have a competition between densification and grain growth. And if we get the temperature profile just right by repeating these pulses, we can achieve dense material. So material very hard to look at the grain size. They are very fine grains. So we are looking at almost no grain growth up to, or very limited grain growth up to 97, 98% of relative density. So this approach can be used for sintering these particular materials, but I think in the future maybe need to develop some more robust process where essentially we correlate the temperature distribution to the grain growth and densification. It means that we do the reverse way. So by knowing the activation energy for grain growth and densification, then we design the suitable temperature profile in order to achieve our target microstructure. Another things I want to mention to you is about what might look like the future perspective and how we are considering these hybridized sintering techniques. So hybridized sintering technique means that we consider combination. So we look at cold sintering, so where we have enhanced solubility because of the presence of this solvent. We have electrical field that support jaw heating, but I might have also additional effect. Then we have application of pressure and we have application of external heating. And these are all effects that enhance the densification of our materials. And so we look at we well understand that over the past 2 decades, research have developed novel sintering technique, and some of them contains one element of one particular technique, but then maybe for a further processing step, they include an additional element. So what do I mean? Maybe researchers have done work on cold sintering of, say, alumina, follow up by ultra-fast firing. So this might be a good way to achieve translucent or transparent alumina using this combination of techniques. And so essentially we have some sort of diagrams of the different techniques. This is clearly the state of the art, but we haven't got through a full rationalization of when to use a particular technique for a given processing step and how to order the processing step in order to achieve the target performance, but also reduce massively the consumed energy. So I'll give you one example, which to me is quite interesting. So this is the flash cold sintering of zinc oxide. So what happened here, we had a combination of water and electricity. So if we have an electric field and we have water, we have electrolysis of water, we have hydrogen and oxygen developed. So I suspect that the hydrogen is sufficient to generate the reduction. The reduction then trigger the flash sintering process. Essentially, is not the most scalable technique, I would say, but essentially able to sinter zinc oxide without the need of an external source. But clearly we have essentially what I showed you in the previous slide. We have an overlap of different effects during the sintering of these particular materials. Another approach that might be a bit more sensible is to combine isostatic sintering, cold isostatic sintering, with the ultra-fast firing. So essentially, we have a standard isostatic press, which normally is dry, but what you decide to do is to add a small amount of moisture to the sample and then do an isostatic pressing, and this allow for translucent sample when we use the conventional sintering. And this is mostly because we have a shift down in the sintering temperature, so limit the grain growth. If we combine together the isostatic pressing with the ultra-fast high temperature sintering, then we start getting materials definitely of interest because we have already using this fast firing technique an inline transmittance of 28 or nearly 29% because of the fine grains combined with a high densification of this transparent aluminum. So essentially, what the message to take home is that by using the combination of different sintering technique and use them, bear in mind the minimal energy consumption, we can still achieve property that may be comparable with much more complex machine, for example, vacuum sintering or microwave sintering to process this type of ceramics. So I would like to conclude essentially that there is plenty of room to develop novel filing sintering technique. And apart from the processing, nowadays we need to worry about recyclability of ceramics. This is a fairly new topic, but I think these new techniques fits well within the scope. And we show that this powder UHS base has great promise to reduce carbon footprint, but also make fairly large samples. So we are working, but on some papers, and essentially we being able to achieve firing of large alumina parts using only 5 megajoule a kilogram. This is a big achievement. Hopefully, we'll publish soon the results. And likewise, for the green manufacturing, we are open to new combination of sintering technique, and researchers are invited to use their own approach. So there is a plenty of room for creativity in order to develop the next generation of firing techniques. Clearly, we see the big scope for hybridite, so merging the different sintering technique together. But this should come with a clear motivation. So why we are doing that and what is our scope? I assume that my time is up, so I will give some time for question, and thank you very much for your attention.
A lot of thanks, Professor Grasso, for your great speech and lecture. And please, your questions. Anybody wants to ask questions?
I'm Andrei Ragulia. It was a pleasure to listen and learn a lot from your presentation today. Thank you very much. In fact, the processing of different sort of materials, including ceramic materials, is developing pretty quickly around the globe today, and you listed many new processes. But my question is about grain boundaries in all these sintered materials, because grain boundaries usually considered the heart of any functional ceramics or functional materials. So, and to my mind, it's necessary to spend some time to prepare well defined grain boundaries in any materials, just to achieve properties which are stable, which do not change during exploitation, and therefore the structure is going to be defined very well, to my mind. So my question is about grain boundaries in the ultra-fast sintered materials. I very much grateful to present sintering of graphite in pure form. This is amazing. This is amazing because this is covalent bonded material, and it's necessary to introduce into to intimize the contact between particles. Even at 1 GPa, it's not sufficient to bring all together carbon atoms in between one sheet to normal interatomic distance. So nevertheless, again, I return back to the question about grain boundaries in your materials. You sinter it very fast, So do you have any comments or observations what is going on in interfaces in any materials? Yeah, thank you.
Yes, so that's a very good question. And clearly, depending on the thermal profile, right? The thermal profile can control the distribution of segregation at the grain boundary. So let me give you one example. So we were comparing fast-firing alumina with the conventional sintering, and we were using magnesium oxide as dopants. So if we use slow heating, the magnesium oxide would diffuse within the grain boundary, and so we were seeing very severe grain growth. When we were using this fast firing, the magnesium oxide was still sitting at the grain boundary. So this means that if we want a metastable grain boundary, then we will cut the processing at a certain period of time. If we want the magnesium oxide or the segregates at the grain boundary to be fully diffused, we need to prolong the holding time. So we have this flexibility to achieve one microstructure over the other. Then what happened when, in particular, what happened when we maybe use more complex heat waves? So we always think about heating up dwelling, but there is no good reason, or there is written nowhere apart from the furnace design. So the furnace won't be able to go up and down the temperature, but the material might be happy to do so. So in that case, it means we need to use more complex tools in order to define the grain boundaries. So for example, we are looking about integration of a novel sintering technique with microstructure analysis, machine learning, the whole things combined together, then might be leading us to predict properties. And as you say, sometimes having a certain type of grain boundaries might be conducive to certain properties, or maybe we have opportunity to have very unusual type of grain boundary or structure that might be suited for different kind of application, essentially. But you make a good point. But since we have newer tools and we are essentially changing the firing schedule, we should look for room for making new properties out of the combination of a new sintering technique that we have available.
Thank you, Professor.
Thank you.
Thank you, Professor Grasso. We have to work in our schedule, and we continue our session with invited speaker, Petre Badica from National Institute of Materials Physics, Romania, with a speech about diboride-based ceramic materials with strengthening and ductility at high temperatures.
Thank you very much. Can you hear me, please?
Yes, we hear you.
Oh, great, thank you. I try to start my presentation. Okay, can you see?
Not yet.
Not yet, okay. Sorry, 1 second. Okay, how about now?
All is okay. You can start.
Oh, great. Thank you very much. Good afternoon. I'm very happy to be in this conference. I see a lot of friends Previously also hello to Salvatore. Hope you are doing well, and it's my pleasure to be here showing some of our results. The idea of this presentation is to look a little bit on materials. So Salvatore previously was looking on techniques for preparation of ceramics. In my case, I'm looking a little bit on materials, and here the key point is related to structural, but not only materials, so mechanical properties in general. So if we look at the current market, we can see that it's dominated by structural materials such as steels, nickel-based super alloys, aluminum, and titanium alloys. So the point here is that if we increase the strength, if we want to increase the strength, we need to get higher density. This is one issue. Second is that these materials, you can see on my slide, they can work up to certain temperatures, which are in between 400 and 1100 degrees Celsius. So if we want to go at higher temperatures, we need to think of new materials. And of course, one general problem is related to this so-called strength ductility trade-off. It means that in principle, if you want a material to be with high strength, then you are not getting ductility, and vice versa. So at the same time, it's very difficult to get these properties. So it's of course interesting to search for new high performance, high temperature materials, and of course there is a lot of literature and effort, for example, with molybdenum, tungsten, tantalum, niobium alloys. There are also works on eutectic alloys, on high entropy alloys, on metal matrix composites. And also there are coming into play some new type of materials, new candidate materials, which are currently difficult to, let's say, to define, the so-called heterogeneous systems. The keywords in this kind of heterogeneous systems are hierarchical or gradient or other words similar, but still, as I said, not very clear what does it mean. There are already some review papers. I indicated them on the bottom of my slide. And we will try also to get into this play a little bit, considering this kind of heterogeneous materials. After all, any composite, it's also kind of heterogeneous system. What is interesting about heterogeneous materials, and this is what Professor Agulia was asking concerning grain boundaries. They should be defined, well-defined, or in some cases, maybe it's better not to have well-defined. Apparently, in these heterogeneous materials, grain boundaries can be less defined. But again, this is difficult to define exactly what does it mean, well-defined, not well-defined. The idea and interesting point here is that in this kind of systems, you can get synergetic effects. So if you think in terms of two materials with different properties, if you put them together, you can get some new properties, and this is very interesting for functionality. This kind of approach, of course, it can be done for mechanical properties, but it can be done for any kind of properties, such as electronics, spintronic, whatever. And the interesting point also here is, in fact, that we are talking about microstructure on one side, which is, of course, fixed because the material is defined by this microstructure. But then we are talking about the response of the material to excitation. And then we are getting different patterns which are partially or somehow overlapping with microstructure. But we should make a distinction between those patterns from microstructure and the patterns from the response of the material. So we can think, for example, patterns of strain. It doesn't mean that in this case we cannot get a combined effect of the components. And interesting thing is that, in fact, many materials from nature, they show such kind of non-homogeneous structures or very complex structures with some kind of organization. I put here some examples. For example, we can see wood. It's very simple to understand that this is a complex composite to some extent, organic material, but we can also look at inorganic materials, such kind of different shells and pearls and all kind of other materials we can find in the nature. But we can also see very complex structures from geological background. So we can try to mimic, to replicate some of those ideas, because these materials might have, and they all sometimes show absolutely amazing properties, which are difficult to be obtained in our artificial systems. The sciences and principles concerning this kind of mimicking, so bionics and geonics, are taking a lot of, let's say, interest today. But there is also some drawback, because many of these natural materials of interest are obtained within very long periods of time. So, for example, to grow some tree, it takes years, or it takes thousands or even 100,000 of years to make some mineral. So from the perspective of industrial application, it's big trouble. And of course, we need to learn from nature, but we should also try to adapt to current conditions. So these kind of materials and designs should be easily fabricated. So we need preferably cheap technologies or established technologies, or somehow technologies with, let's say, economic output. In our case, we try to use spark plasma sintering. So Salvatore already did an excellent job to explain different things about spark plasma sintering. I will not insist. It's a technique far away from equilibrium with some specifics. These specifics can be very interesting and useful. And of course, there is a lot of work to be done to improve and to adapt and to make also integration of this technology with other industrial technologies. So next, I would like to show you 3 examples which contain diborite. In this case, here we have a superconductor. This is MgB2 superconductor. Of course, this is not for high temperature applications. This is for low temperature applications. And in this case, the point is that in principle, it's a kind of ceramic. Of course, it is brittle. It's not, it has no ductility, but to make into complex shape, it is very useful. So what we did was to try to make a superconductor in which we added graphene or boron nitride hexagonal. We obtained a kind of composite. And this composite, because graphene and BN, they have van der Waals bondings. These are the places in which we can try to make machining by chipping. So this material it's becoming very convenient to obtain different shapes. And you can see some examples presented here. On the other hand, this kind of material is, it has very good superconducting properties. For example, here we have trapped field. So we use as a superconducting magnet. So the trapped field here, it's beyond 3 Tesla, which is pretty good considering that the normal magnet is somewhere, normal commercial magnets, or neodymium iron boride, it's about half Tesla. So it is an interesting thing, and this material is also machinable. Okay, next example, it's about this titanium diboride boron carbide. And if we look at the microstructure by SEM, we do not see something very special. It looks like a kind of 3D interpenetrated microstructure according to classifications, but it has very interesting properties. And I am showing here at 1800 degrees how this material is behaving under bending strength, under bending load. So you can see there is an elastic part, the A part, then there is a ductility B part, and then there is a strengthening C part. And at the end of this, before breakage, we have a bending strength pretty high, as you can see from my graph. So the question is, what is going on? I mean, it is quite unusual. So we started to look in detail by TM on this material. And it's interesting to see some defects in boron carbide. Actually, there are some stacking faults and twins with some orientation, but in the area in which the fracture occurred, these twins, they show different orientations. So we tried to come up with a model. And this model is based on the fact that these planes we observe for stacking faults and also for dislocations. If we look at the crystal structure, these kind of planes are orthogonal. So what is going on is that if we, let's say, squeeze the material, to some extent, material is responding in elastic way, but at some above a certain load, it's becoming ductile due to defects, induced defects, and different slidings. And these slidings can go up to a certain level, and then through shearing, they are locked and strengthening occurs. So this is our image to understand this kind of bending curves, very unusual bending curves. Of course, the question is, what is doing here titanium diboride? So for the moment, I do not have a good answer, but anyway, it's a system. It's clearly, there is also some contribution from titanium diboride. And the last example I would like to show, the third one, is this high entropy diboride material. It is, the key point here was to try to make this material by powder metallurgy, because usually people are doing such kind of materials by melting. So we considered exactly the heterogeneous concept I explained at the beginning. So we were mixing diborides and mixing them relatively poor, and then making spark plasma sintering. And this kind of material is showing very interesting mechanical properties. You can see on the right side, the bending strength is actually increasing with temperature, not decreasing as expected for many materials. And moreover, at 2000 degrees, we have a kind of ductile or plastic deformation mechanism. Then, of course, we tried to look on the microstructure. And if we look at the microstructure from the macro level with SEM, we see that material is a kind of composite. So there are There is a matrix, and in this matrix there are this kind of large grains. And these large grains, they have a different composition, but still it is a diboride. So if we go back to X-ray diffractions, we can see that actually all the peaks, they have a kind of shoulder. So this is a kind of good agreement between the two results. So to understand further what is going on, because of course this kind of material and this kind of microstructure cannot explain our behavior in mechanical properties with temperature, we went to try to see in detail in TM. And here are, for example, samples at room temperature, so before bending and after bending. And you can see that there is very unhomogeneous structure. And we believe this is extremely important. So in here, we can indeed again see that we have grains which are, for example, rich in thallium and poor in titanium, and vice versa. So it's a kind of two-phase materials in the macro sense, but it is a material which is, I will be back, which is composed of multiple diborides with graded and very diffused interfaces. So exactly what Professor Ragulia asked. So it has not a clear grain boundary, and this might be very important. This material is not only showing this kind of behavior. So one grain has a very different composition, but also this kind of composition, you can see here that dislocations on the left side are changing. The density is changing depending on in which region of this grain you are. So this kind of information is, let's say, supporting this idea that this non-uniform condition can give you mechanical properties very special. Okay, finally, I would like just to say here that if we go to nano size, there are experiments showing that in some materials, in some ceramics, if you make, for example, compression test on nano samples, you will also see plasticity. This is very interesting, although in the macro scale, these materials, of course, are brittle and hard. So this kind of example with this complex diboride, it's showing that it's somehow possible to transfer from nano to macro. You can have a chance to transfer this kind of unusual properties. So design of material, it's and the microstructure, of course, there is work to be done in this direction to understand all these things. Here, it's there are different types of microstructures, and our material is on the right side. So this is a kind of model between what is going on between the red and blue phase. So you can see this graded, diffused grain boundary. And this material here with blue, we compared with other diborides from the literature, and you can see how it is, how are the properties. So basically, as I said, there is an improvement with temperature and then a ductile behavior. And the other diborides, complex diborides, they show in most cases a decrease with temperature. So I'm arriving at my conclusions. And I would say that what we've learned from this work is that we need to look at the materials at different scale. So from nano to micro and even higher scales. The principles and criteria to design materials in which we want to combine strength and ductility are not yet fully established, but there are good chances to go in this direction. We also have shown some kind of unusual new type of microstructure And this is obtained by powder metallurgy. So if people are considering only melting technologies for example, for this type of high entropy materials, probably it is also interesting and useful to go to powder metallurgy aspects. Another idea is that scaling up from nano level to other levels, it is also a big trouble, and it's very interesting to do that. And finally, I would say that these materials, we investigated, you see that they have very unusual properties, but the number of elements, it's 5, while in the literature there is a push these days, and I think high entropy alloys now are even with 8 elements. So the big question here is, do we really need so many elements? Thank you for your attention. And these are my colleagues contributing this work. Thank you very much.
Thank you, Professor Bodica. And do you have any questions, dear participants? Please. Here you.
Professor Bodica, Alexander Vasilyev here. Thank you very much for a very interesting talk. I have actually a few questions, if I may. The first one is the titanium diboride boron carbide composite and the strengthening at 1800 degrees. Yeah, something like that. So you said that titanium diboride's role isn't clear for now, and explained the strengthening by boron carbide only. Are there any data on the similar behavior is there in pure boron carbide at the same temperatures? Because if the mechanism are boron carbide dependent, it should manifest in pure boron carbide too.
So for boron carbide, we couldn't see similar, let's say, unusual or very unusual behavior. Concerning titanium diboride, one problem with this material is that apparently with temperature, the disappearance of these locations is very fast. So titanium diboride and zirconium diboride, due to let's say their intrinsic crystal chemistry, apparently they can somehow, these locations can vanish with temperature. There are few works which are showing something concerning these locations in titanium diboride with temperature, but I would say the information, the critical information and the amount of information is not enough to make any kind of good judgment, including in our material for the moment.
Okay, so it's actually maybe the question wasn't, maybe I didn't put it clear. The question was more about boron carbide. Is it possible that because the mechanism was in terms of boron carbide, worth looking
yes,
the same mechanism there?
Yeah. Yes, I think it might be possible. You know, this material is a very complex material. Even the crystal structure is not well resolved, especially if we are considering that the stoichiometry of this material is not fixed. So we are talking about boron for carbon in general, but in fact, this material has a very large domain of stoichiometry. And in this situation, if we look at what is going on there, we have some kind of dodecahedrons connecting through some bridges. And these bridges they might have a strong influence on all these mechanics. It's very difficult to look at the local level. So we need to assume some kind of average. And on average, it's approximately what I have shown you. We need to study more. Maybe it's possible, but again, at every time we need to be sure what kind of boron carbide we are using and what is going on during the processing.
Thank you. I was asking specifically because one of my students, Vladislav Billy, unfortunately, he presented his talk yesterday, and it's related to strength in boron carbide. And probably we could look into the issue also with, he's doing computational works, and we could probably look into that with modeling.
Yeah, this is very good. If possible, also to compare with experiment would be absolutely great.
Yeah. Thank you. And one little.
Yes, please.
High entropy with high entropy diborites with powder metallurgy and the fuzzy interfaces in there. Is the diffusion actually sufficient to get these fuzzy interfaces at this temperature? It's 1800 degrees or something like that.
Yes, it's up to 2000. One issue here is that if we use titanium, we use diborites mixed materials. So this is one issue. Second issue is that all these diborites, they have a little bit of different crystal chemistry. And of course, different melting temperatures because of that. They also have different sizes. So the idea is here that kinetic factors will be important. And what we have observed that the material is kind of stabilized from synthesis. So there are no important changes afterwards when we heat up for the bending measurement. So it's a kind of, let's say, not fully stable, but stable enough for some application, or at least we believe at this moment it might be useful. We need to go further, making long-term cycling probably with heating and cooling and things like that, and observe what is going on with this material. If this is positive, then indeed this kind of properties can be stable for a long time, then applications are very useful. Right now, I don't have a good answer to this, but at least for this experiment, they were stable.
Thank you. Thank you very much.
Thank you,
Yep,
Professor.
thank you.
It was two very interesting lectures, and our schedule a little bit shifted. Okay, we continue. The next one is Rimvydas Stonis from Laboratory of Composite Materials, Lithuania. Are you ready?
Hello, everyone. I'm
Hello.
Tadas Bekeris. I am the presenter of this presentation.
Start your presentation. Yes, of course.
Okay. Can you see the slides?
Not now. All is okay. Yes, we see. Start your presentation.
Okay. Okay. So hello, everyone. I'm Tadas Bekeris. I'm second year PhD student and from Vilnius Gediminas Technical University, Lithuania. Today I will be presenting a topic in which I will be looking at some test results, which corresponds to my research and development of environmentally friendly refractory material using mineral stone wool production waste, also known as cupola dust. So start with, we have a research problem in Europe. We have 43 mineral stone wool factories that are using cupola furnace technology, in which 3.6 million tons of mineral stone wool products are produced annually, and this sector is growing by 3% each year. And during this production, using the couple of furnace technology, a dust is generated in the melting process. So the dust flows with fumes out of the furnace and is collected in filters. This dust corresponds to from 2 to 3% of annual production, which means we have from 72 to 108 kilotons per year of this dust. And in Lithuania, we have one factory, and which generates 2.5 and 2.7 kilotons per year of cupola dust, which have no secondary developed usage, and it's disposed to landfills. So previous studies of my supervisor Rimvydas Stanys have shown that this dust have an effect to change mineralogical structure when heated. So at 700 degrees, we have a spherical. This dust has a spherical mineralogical structure, and at 800 degrees, we do see that it changes to needle-like structure. Therefore, this study showed that only up to 3% of dust can be used. So my study is to take this dust, apply liquid, and using different liquids, create granules out of this dust. So as research methods, granulation was made using Irish type mixer. XRF, SEM, XRD was made by a specific machinery. Bulk density, electrical conductivity tests, colorimetrical and exothermical according to standard methodology. So to start with, we have calcium alumina cement. We do use for our studies Istra 40 as the main binding material. We do have cupola dust, which chemical composition is shown below. We do see that this dust contains a lot of silicium oxide, magnesium, kalium, sodium, ferrum, and to create granules, in this study, we use 3 different liquids. So H granules corresponds to water, N granules corresponds to sodium silicate liquid, and D granules Divacil. When created the granules, we sieved them and grouped to 3 different size groups. So A is the smallest group, B, then C, and D, which has their own granule sizes. We have then tried to heat them and see if the mineralogical structure change remains. So we do see that the granules also change the mineralogical structure to needle shape like. We have determined the bulk density and granulometry of these granules. We do see that cupola dust corresponds to 3 to 7 kilograms bulk density, and then granules have an increased bulk density. We do see that a significant increase in N and D granules, which corresponds to the bigger density of the liquids used for granulation. And also we do see that a lot of that all granules show are uniformal distribution among the size groups. So we have started our research by determination of electrical conductivity. So in the blue line, we see the dust. It gains the maximum electrical conductivity value at the very beginning, and the electrical conductivity doesn't develop over time. So small particles release dissoluble ions and so on. And when we tested the granules, even though we have started with H granules, so with water, we do see a slightly bigger electrical conductivity value. However, the development of the maximum electrical conductivity value depends on the granule size. So the bigger the granules, the slower the maximum electrical conductivity is reached. Then we have made the same test with N granules and compared them with H. So we do see that the same tendency for the development of the maximum value. However, we do see that N granules have a lower value of electrical conductivity compared to dust and H granules. Then with D granules, we do see even lower electrical conductivity value and also the same effect for the granule size and development of the electrical conductivity. Then we have started colorimetry tests, and we have started them to see how the dust sorry. Sorry, my presentation. Sorry, I have a problem with my computer. Do you see the slides?
Yes, all is okay. You can continue, but a little bit briefly, if possible.
Okay. Okay. So, and when we incorporated the dust to replace dust with calcium alumina cement, we do see that it accelerates hydration of the cement, and high quantities of replacement don't have a huge, significantly reduced heat flow. However, when we replaced calcium alumina cement with H granules and compared them with dust itself, we do see an improvement to the hydration. Then when we used N granules, we do see that it affects hydration differently than H granules and P granules. So it accelerates the hydration and also gives bigger heat flow curves and initial heat. Then when D granules, we do see that it gives even small quantity gives even bigger heat flow value than the control samples. So and the bigger and it performs that bigger quantities change the hydration to and pushes it to later on. So then for exothermical reaction, we have tried to mix the granules fractions And we did see that when we do not use one fraction, like in the colorimetrical study, we have used only the smallest fraction to see what if the difference is between the how it affects the hydration compared to dust. So we do see that using different size groups in equal amounts, the hydration, even with aged granules with water, we do see that the hydration happens more locally to the control sample than when we tested the same on N granules with sodium silicate. We do see that it happens in a really narrow time and near the control sample. And also when D granules are used, so the Divasil, we do see that every samples happened at the same time as the control sample, the hydration. XRD also was performed, and even though it's not done yet, we do see that the aged granules are changing minerals when heated up to 1000, and when 500 when heated to 500 we see just a small mineralogical change, and when the heat is up to 1000 we do see a big difference here. So for the conclusions, we just started with this research and evaluated the possibilities of granulating the cupola dust and potentially utilize it at large volumes of this dust to incorporate it in high temperature composites as a filler. And also we did see that granules influences calcium alumina cement hydration differently than the cupola does it is. And also the effect differs from liquids used for granulation and also granules fractions. So when we mix the granules fractions, we do see that we can control the hydration time. So for further research, these tests are really helpful. So, okay, thank you very much.
Thank you for your report. And anybody have questions? Dr. Vasiliu, because no. And I have a question. Maybe I'm lost, but where you use your granules finally? Application of your material.
Yeah, so the main idea is to incorporate these granules to the calcium alumina cement and use it for refractory purposes as a filler. So we will be creating and cement for refractories that will work as a thermal insulator.
Okay, it's the next step, and I hope on the next conference you report the properties of this cement. Okay, thank you for your report, and we continue our session. Please, Pavlo Markovsky from Kurdumov Institute for Metal Physics, Advanced Satellite Titanium-based materials, 3D printed with electron beam and wire approach.
Second, next slide, and third, previous slide.
Thank you, Mr. Chairman. My presentation will be a little bit different because it is dedicated to metallic materials, layered materials which have layers of with metallic matrix reinforced with fine ceramic particles. And this is because of lack of time, this is very brief overview of our joint work with my colleagues from company, private company Czerwona Chwila, and from Military University of Technology in Poland, which summarized current situation of our continuing works in the field of how to produce more efficient materials with reduced weight, for which materials should be more efficient for protection against ballistic projectiles. And first of all, we are working with titanium. Why with titanium? Because titanium already used for a few decades as armor materials for different wait, sorry. Sorry. First or second? This is not. I see. Sorry. Titanium already used for many years as armor materials for different applications because, first of all, it has at least 1.7 times lower weight as compared with steels having the same strength. This material is corrosion resistant, non-magnetic, and in comparison with different materials, first of all with ceramics, has much better high toughness of fracture toughness as compared with different materials. But at the same time, it has disadvantage like insufficient hardness, because maximum which can be achieved in the best titanium alloys by any type of heat or thermomechanical treatments is not more than 380 HV units of HE. At the same time, usual armor piercing projectiles has strengthened steel cores with hardness not lower than 780 HV. And that is why it is necessary to find possible ways how to increase this hardness of these materials. And first way is to add any type of hardening particles into this material. We spend a lot of time trying to produce metal matrix composite on the titanium base, hardened with carbides or barides using powder metallurgy approaches. And we reached some success in this direction, but powder metallurgy approach is very restricted in capability in sizes of produced materials. At the same time, real application required much bigger produced parts. That is why we try to apply to produce such layered materials with strengthened composites using 3D printing technology developed by Czerwona Chwila company. Their invention is following. They used a new patented method of heating by conically centered electron beam with feeding of wire from in the center of this conic this conic electron beam. And this technology allowed them to produce from titanium wire different kinds of different kinds of products, including the semi-sphere, cell structures, or even long bars for real application. So they not only developed this technology, but also produced different equipment for realization, so, starting from laboratory scale and industrial scale, big installations, which we all of them we use it in our experiments. But very important input into this study was made by our colleagues from Military University of Technology, because they have very good equipped ballistic laboratory and standardized by NATO standards, and very well qualified personnel. Here you can see examples of materials which we produced using this 3D technology. We started from uniform titanium 6 aluminum 4 standard material. We used it like reference materials for comparison with our layered materials. Also, we made materials, layered materials, which consisted from layers of different composition titanium alloys. Then we produced multi-layers materials which has reduced, more reduced than titanium, solid titanium materials density. You can see density is only 3.9 gram per cubic centimeters. And here you can see several examples of samples which two layers samples which have basic layer of rolled titanium 6-4 alloy with printed metal matrix composite of different composition. Some of them are strengthened by titanium carbide, another with titanium barite, and some of them with both carbide and barite. Special attention I want to pay this material. This is 3D printed layers of 6-4 materials and metal matrix composite printed over the porous titanium, which that allowed us to reduce density of total density of these materials to 2.9 gram per square cubic centimeters. And now I want to show you some results, some separate results of ballistic tests of this material, of titanium, different titanium materials. We started with conventional rolled plate of this alloy titanium 6 aluminum 4 materials. This is commercial plate having thickness 14 millimeters, density 4.5 gram per cubic centimeters. You can see that testing with 7.62 armor piercing bullets NATO standard, we received result like standard measuring of so-called V50 parameters for evaluation of ballistic resistance of materials. First three bullets was not pierced this plate, but fourth pierced. And compare with results of testing of our materials. 12 millimeters total, 12 millimeters of two-layered samples with layer of metal matrix composite, and even 10 millimeters total with metal matrix composite printed on the top. You can see that even on a rare site, there is no serious evidences of any damage. You can compare it with rare site of this plate. And this is that material with porous layer inside. And result of this test, you can see that bullet was stopped even inside porous layer. And here you can see some frames for rapid video records how bullet come into this sample, and after the fracture of the bullet, remnant some fragments of hard core was ejected out. And this result was described and just published in this journal, Scientific Reports, where we showed that such materials not only they stopped the bullet and broke this core, but due to presence of porous layer, it absorbed kinetic energy of impact of bullet. So this is example testing only few tests of our 3D printed materials tested with much more stronger projectiles, these 12.7 millimeters armor piercing bullets. These two variants, this is single materials, single composition titanium 6-4 materials, which about I told previously. It was stopped such kind of bullets starting from the thickness 40 millimeters. 35 millimeters thicknesses of three different alloys, 3D printed titanium alloys, not composites materials. Also stopped, was broken, but core of this hard core of this bullet was also stopped. And here you can see first experiments made with three layers materials with very thin surface layer of metal matrix composite strengthened with titanium carbides, which was made in this laboratory private company in Poland. This company Precisia. Can you start this short movie? Yes, you can see that our materials withstand, and hard core of this bullet was stuck in our material. So now I can show you comparison of different titanium materials which were tested by us, and also usual titanium alloys, conventional titanium alloys tested by other authors. For example, John Fannin from HighMatTech Corporation, Research Laboratory of HighMatTech Corporation, this line, dash line and field around it, number 1, corresponds to commercial titanium alloys with various composition, microstructure after various types of treatments. And you can see that penetration depth depends on linearly depends on specific kinetic energy. When we tested, as I told previously, we have some experience in the preparation of metal matrix composites by powder metallurgy methods. This field moved to less deep penetrations. But when we add to these sintered materials special methods, for example, hot isostatic pressure, it also moved to smaller depths. And the best result we obtained by layered materials printed with electron beam and wire. I forgot to mention that we specially designed this wire. This is cored powder wires of our special composition. And here is comparison. Oh, sorry. Wait. No. Oh. Here you can see comparison of our several our materials. Titanium, this is powder metallurgy printed by powder, sintered with powder metallurgy with subsequent hot isostatic pressing. After the testing with the same armor piece and bullets, you can see difference between our titanium alloys with usually used armor steels, Armox 600ST and Armox 500ST, which has almost about 2 times bigger specific weight. And at the same and also this is result of testing of commercial ceramic plates used in real bulletproof vessels for soldiers. And you can see that each shot make a crash of not only the one fragment of this in this structure, but also neighboring fragments too. Here I just want to show only a few selected publications in which who will be interested can find more details. I nothing told about microstructure investigation, our investigation of phase transformations in these materials during the printing, heat treatments, and also during the testing. But we did everything, but I have not too much time. And conclusions, I just want to say the main conclusion that we already have technology developed, technology and materials for producing such materials, which are very promising from point of view of efficient protection against such projectiles, hard projectiles, and efficiency is much better than if compared with steels or pure ceramics, and possibility to employ inside these materials porous layers allow it also not only stop the bullet but and absorb kinetic energy of such materials. Thank you for your attention.
Thank you for your report. Very interesting report. Is any questions? Please, Dr. Vasily.
Thank you very much for an interesting results presentation. I have maybe you said this in your presentation. Maybe I've missed it, but I remember that the density of the material is somewhat below 4.
Yes.
It's volumetric density. How about the superficial?
Sorry?
I mean, what's the weight per square centimeter of the effective?
Per cubic centimeter.
No. Per cubic is clear. It's under 4.
Oh.
But the armor, armor plate,
I understand.
could be
Weight
10 centimeters
meters,
thick.
you mean?
Huh?
You mean weight of square meters?
Yeah. Yeah.
I cannot say just now because we not produced real, for example, plates for vessel, bulletproof vessels yet, because we are on the stage how to optimize thickness of these materials between printed layer and basic layer. For example, we made some experiments, and these results very first approximation. It will be printed in last issue of our journal Progress in Physics of Metals, but in parallel, we just started with also with our Polish colleagues special numerical modeling researches. We are only the first stages, but for example, from our first approximation, thickness of 10 millimeters of our materials is staying better against the 7.62 millimeters armor-piercing bullets than 6 millimeter 6 Armox still. So it means that comparing specific gravity, our materials will win in competition with this steel in weight of square meters. But
just a little.
It will be much.
Just a little, but I mean that it's not twice as thin.
No,
or as thick, but it's much more complex in production, so it's much more pricey than armor steel.
It's more expensive, as I told just now, but what is the price of people's life?
Perhaps armor steel? I mean, in these tests you showed, what was the thickness of the tested plate?
Which one?
Yeah, the one you compare with the existing.
Here, 10 millimeters.
10
millimeters total. Better than 6 millimeters Armox, the best of Armox. Because
now that's really close to parity between the two materials. Could you go back to the slide you are showing? The one on the right, which shows penetration up to the ceramic filler. Yeah, am I right?
Ceramics on the top, metal matrix composite. This is layer of 6-4. Porous, this is only supporting 6-4 layer, not ceramic.
And the middle one?
Thickness, I don't remember, 25 or 27.
Yeah, it looks a little bit thicker than the ruler you have in front. And the ruler is typically up to an inch, 2.5 centimeters. If I'm not mistaken. So
yes, but ruler is laying on the table, but sample is higher. All data available in this publication about thickness and so on.
Thank you very
much. I don't remember.
Thank you for very interesting talks. What is porosity layer
Porosity
materials?
of this layer?
Так.
Less than 60. Sorry, less than 50.
50.
50.
This is well for you?
No. This is printed on both sides of the porous materials which we made using powder metallurgy approach. It was printed by this 3D printing method using the conventional titanium 6-4 wire. And only after that, from one side was printed metal matrix composite.
Oh, understand. Thank you.
Thank you, Dr. Barkovsky. And the next speech, Alexey Barbara, supermagnetic state of cobalt nanoparticles in granular films based on dielectric matrices, aluminum oxide, silicon oxide, and titanium dioxide.
Thank you, dear participants. In this presentation, I would like you to introduce the specific of supermagnetic state of granule films, as well as a variety of parameters that can be extracted from magnetic features. Size effect is the heart of nanoscience. It's more true for the magnetic nanoparticles. With reducing the sizes of nanoparticles, surface energy becomes more than volume energy. So breaking down on domain structure is energetically disadvantageous. So such little nanoparticles stay at a single domain and then transfer to the supermagnetic region. The transition in supermagnetic region occurs where the anisotropic energy of such little nanoparticles comparable with thermal energy. And this anisotropy energy associated with effective anisotropic coefficient with material parameters and volume of such nanoparticles. Supermagnetic nanoparticles have a twofold nature. For the data storage devices, it's parasitic and negative parameters because we have the lost magnetic order in such little nanoparticles and becomes a loss of data. To supermagnetic limit of such parameters, it's 60 kT. So to obtain the data density near 1-2 terabit per square inches, we need near coefficient energy is more than 10 and 7th power, with medium diameters near 5-10 nanometers. Another side for biomedical application, quick switching from magnetic and non-magnetic state is crucial. So we need less parameters of coefficient anisotropy near 4 to 5 power with medium diameters near 10 to 12 nanometers longer. Our films, what we work in, its parameters consist from cobalt nanoparticles distributed in 3 various matrices: alumina, silica, and titanium matrices. They conducted electron beam physical vapor deposition methods on alumina substrates and 6 our granule films from 1 to 5 micrometers. Specific of these particles because they separated matrix media. In our case, it's more amorphous and in the latent barrier of coating of these nanoparticles. One of these parameters with increasing concentrations, the sizes of cobalt nanoparticles increases. So these parameters is we can control it using sizes of nanoparticles. In this study, I focus on determining two parameters. It's coefficient anisotropy of nanoparticles and correlation between sizes and magnetic parameters. First of all, it's the first principal information from magnetic fields giving us only basic information. So we need some theories that extracted the internal parameters of coefficient of anisotropy. As we see on the this graphic, the becoming of blocking temperature appears where temperature energy Kt comparable with anisotropy energies. So with above the blocking temperature, these nanoparticles stay superparamagnetic with no remnant magnetization, and we can describe this course by Langevin method. For the below temperature, blocking temperature, in blockage regime, and we appear the hysteresis loops and magnetization described by low approach to saturation method. So we have two distinct methods which describe one parameter. So we can compare this with high accuracy. First of all, talk about Langevin method. On slide you see the fits of magnetic parameters. Using this formula, we can extract the volume of magnetic nanoparticles, and for the near-spherical nanoparticles, we can calculate it. We compare this data with scanning electron microscopy parameters, and you see that in the good accuracy compared is diapason from the same parameters. Below the blocking temperature, such parameters, nanocomposites described by the low approach to saturation empirical formula, which consists of such parameters. Parameter B also effect on the coefficient anisotropy, and we from the fit extract these parameters. These three parameters have specific deviation. It's first parameter A divided in H, deviation from the ideal structure. The second one reflected the anisotropy constants, and paramagnetic-like term indicated supermagnetism of ultrafine nanoparticles. First of all, we can describe how many of these fitting parameters described our structure, and most of all, it's with great accuracy, it's three parameters with reflected godness of fitting. Also, we can keep in mind that the parameter A in this formulas also depends on the crystal structure. So for our cobalt, most of all like hexagonal central close packed, but sometimes for fine nanoparticles, they face center cubic in room temperatures exist. Low approach saturation also allow us to determine the sizes of nanoparticles using knowing the parameters from fit in these curves and the blocking temperature. We also obtain the sizes of nanoparticles. But in our case, we have interesting parameters calculated by last method. When concentration of cobalt increases, we have decreasing of nanoparticles. That's not true. One of the reasons of this here the anisotropy energies. Anisotropy energies consist of various parameters. Its shape, anisotropy related to the shape of nanoparticles, its surface, breaking surface at this nanoparticles, its magnetoelastic and magnetocrystalline. These two parameters is very little and always neglected. But the main contribution is made by surface anisotropy. So we can reflect this that the coefficient, effective coefficient of anisotropy consists of two parameters, volume and surface. So to determine the sizes of nanoparticles, we did not use the effective parameters. We use volume parameters, which reflected the real volume of these parameters. Using this calculation and also extracted the surface coefficient of anisotropy, which lead in the ideal parameter from 0.1 to 1, which coincide with the experimental results for a lot of samples, not only us, but in literature. We recalculated these parameters. This new volumes is better. Consider this. So we need to accept the surface anisotropy when we calculated the dimensions. Also, we interesting parameters. With increase in cobalt concentration, we surface anisotropy coefficient also increased. But when sizes increase, this effect can be reduced. One of the causes of these reasons is, first of all, wide distribution of sizes of nanoparticles in samples. With increasing concentration, which obtained electronic beam vapor deposition methods, coincides to coexist very less nanoparticles, little nanoparticles from 1 to 3 nanometers to big nanoparticles from 20 to 30 for 40 nanometers. And the second is its surface oxidization of such nanoparticles that can be described later. The third method from which we can describe the volume of nanoparticles, it's inverse magnetic susceptibility method. It's very easy because for the above blocking temperature, such super paramagnetic as paramagnetic materials obey the Curie-Weiss law in reverse characteristic coordinates, and from them we have linear fit, and we can also obtain the parameters of volume of nanoparticles, which is described on the table. This method, inverse magnetic susceptibility, also help us to indicate magnetic ordering of nanoparticles. Negative values of this theta angle indicates little antiferromagnetic, which also about oxidization, the value of oxidization of a surface of the nanoparticles. In conclusion, I can consider these three methods. All of above methods help us to determine the sizes of nanoparticles. Legendre method have simple fit with two variables. It's very good for characterization superparamagnetic nanoparticles, but it had controversial accuracy for wide size distribution. For high concentration, we have a little hysteresis loops, which not theoretically grounded by this method. Low process saturation method allows us a very important constant of anisotropy to describe, but to describe the sizes of nanoparticles, we of course can take into account the surface anisotropy parameters. And some minuses, its complexity fit up to 4 variables. Some goodness of fits maybe it depends from your material in these cases. Inverse stability method, it's talk about can allow to determine the antiferromagnetic ferromagnetic ordering of nanoparticles mainly. Simple linear fit, as its graphical parameters or fits. But minuses, it requires the temperature range where Curie-Weiss law is observed. For our much bigger concentrations, it's more than 300 kelvins, and which not our diapason where we are working with this. Thank you for attention.
Thank you. It's any questions for the speaker? Okay, I have a question. I want to ask you about why you thinking your material is advanced composite material, because it's much closer to low dimensional and nanomaterial session.
But they say it's composite materials. I don't know why in this section.
Please.
I wonder if I may ask, whether the choice of the storage image is it so? Are these materials for magnetic disks? Because those are probably already almost in the past.
Yes, I answer without maybe.
Stop on this one. Is it intended for the magnetic disks storage, or is it just an illustration?
It's some sort of illustration because that's the start of this disk. This is the granule materials started, but they not great with thermal stability. And nowadays, and from 207, it's layered structures and all. But this material is experimental ideal. Not experimental, theoretical material, and studied the supermagnetic nature, because for today data, it's need 5 or 6 terabit per inch squares in today's materials. But it's very hard to obtain because without knowing the some specifies of supermagnetic states. In layer structure, they reduced this limit of supermagnetic transition, fixing this specific layers, some 50 layered structure and all. It's some sort of depends on the money and another level of production. So of course, our ground materials can be used in the data storage devices, but as theoretical materials for studying supermagnetic state, it's very interesting materials.
Okay, so the supermagnetism itself can be used as a storage.
Yeah, supermagnetic negative parameters for the storage because they not net magnetization with absence of magnetic field. So it's we need to storage magnetic nano bits. Its names. So they can be less than some parameters. So we can study specific surface addition to this anisotropic process, some form of additional to reduces this volume, reduces sizes where this supermagnetic state occurs. We need ferromagnetic or monodomain structure.
Okay, one small, really small question. Can you next slide, please?
And very brief answer.
Insulating barrier and nanoparticles, yes?
Yeah.
What is insulating barrier?
It's matrix.
What kind of matrix?
We have alumina or silica or titanium.
So it is a composite.
What?
So it is a composite.
Yeah, it's composite.
I think perhaps this is the reason why your talk is in this symposium. Okay, thank you very much.
Okay, thank you. And the next speaker, Andrei Terpakov from Institute of Pulse Processes and Technologies. Obtainment of cuprum titanium carbon system metal matrix composites by spark plasma sintering of powder mixtures prepared by with high voltage electric discharge treatment in kerosene.
Thank you. Good evening, dear colleagues. Can you hear me well? Can you see me well? Can you see my screen?
I hear you. See your presentation. Start your speech, please.
Yeah, thank you. Today I would like to share results on the creation of copper titanium carbon composites obtained using high voltage electric discharge in kerosene, followed by spark plasma sintering of threaded powders. The use of composite materials based on graphite and copper for electric machining of hard alloys and refractory materials achieves high efficiency, but it has many drawbacks, such as the instability of such process and high cost of obtained materials. Copper-based composites transit with titanium carbide particles provide high hardness, high wear resistance, and good values of electrical conductivity if compared to pure copper. However, they are also expensive to produce, and their properties can be compromised by contamination from tool metal particles during mechanical powder activation. Our approach addresses this issue by applying a relatively novel method of powder activation, namely high voltage electric discharge in liquids prior to the consolidation using spark plasma sintering. Sorry. So the goal of our work was to study the impact of high voltage electric discharge treatment on metal powders with the subsequent spark plasma sintering on the properties of obtained copper, titanium, carbon system metal matrix composites. The idea of studies was to use a relatively new approach for obtainment of such composites, which consists in two-stage synthesis. On the first stage occurs dispersion of particles and preparation of surface of threaded powders, and second stage includes the compaction using spark plasma synthesis. So, as I said, intended usage of our composites would be electrodes for electrical machining of hard alloys and other materials, and electrodes for public transportation, and maybe we can see some other uses for obtaining composites. But first, before I go to the properties of the obtained materials, let me briefly remind you about what is exactly the method of high voltage electric discharge, because while it is not new to us, it may be new to some of colleagues. Essentially, this is a high voltage explosion in the liquid, which consists of three main stages. First is pre-discharge stage, when high strength electromagnetic field is applied between the electrodes in the treatment chamber, which leads to the formation of plasma streamer chrome, which grows from the positive electrode in the general direction of negative electrode. In our case, the negative electrode is the discharge chamber, namely its bottom. And when the first of these streamers reaches the opposite electrode, the second stage starts, which is exactly the channel stage where the most effects occur. As soon as the through conductivity channel is formed in the liquid, it starts expanding, and it has a very high values of pressure and temperature. It emits light radiation, which can be used in other technologies, but not in this. And the rapid expansion of this channel, which can reach tens of kilometers per second, the speed of such expansion leads to the formation of compression to compression waves, and in some cases, shock waves. And these shock waves provide mechanical effect on the treated particles, but also if conductive particles are used, the same plasma channel could pass through the layer of powder, which leads to the heating, which leads to the melting and to the vaporization, which also can lead to the dispersion. And when all of the stored energy is released in this plasma discharge channel, the third and the final stage starts, which is called stage of gas vapor cavity pulsation, because in the place where plasma discharge channel was formed, named gas vapor cavity with excess pressure is formed, which starts also expanding, and this leads to the formation of hydroflows, which provide mixing of threaded powders, and also this provides additional mechanical lift. And so this stage can also impact the particles of treated material. And so this is briefly the main factors which can be used in order to achieve mechanical and activation of powders, and also the synthesis of new phases on the stage of the treatment. So our research was conducted at our research stand, which allows realization of different discharge modes. And namely, these modes were, as we call them, single point spark discharge, which provides a relatively high volume of plasma discharge channel, as we can see from physical modeling results. And so this mode provides rebalancing the energy between different impact factors. So in this mode, the most fraction of energy is released in form of mechanical impact. While another mode, which we call volumetric multi-spark discharge, allows us to redistributes this energy, so most of this is released into the plasma between the particles, including the plasma between the particles in the layer. So we can use more mechanical impact, or we can use more thermal and plasma impact. The treated powders were then compacted using our experimental spark plasma sintering complex, which allows us to perform spark plasma sintering using the proposition of a direct and alternating current with total amplitude of 1.1 kiloampere. We perform sintering in vacuum around 100 pascals. We provide sintering pressure up to 50 megapascals. And for copper composites with copper matrix, its thermal holding temperature was 868 Celsius degrees. The sintering time was around 3 minutes, which allows us to provide the synthesis of composites with relatively low porosity without the significant grain growth. Then we performed different studies for treated powders and for obtained composites. We studied powders dispersion. We studied phase composition using X-ray diffraction patterns. Also, we studied composition of obtained composites using also X-ray diffraction patterns. And we studied their hardness, namely Rockwell hardness scale B. Also, we studied their heat resistance. And by gravimetric method. Also, we studied their wear resistance with our experimental custom friction machine, which was based on an electric grinder. And also, we studied their specific electrical resistivity because we intended to use these copper-based composites, as I said, for electrodes for different applications. We performed sintering of reference materials, clear copper powder, 100% copper powder consolidated by our technology, and then a composite which contained pure copper and a different fraction of titanium carbide with initial particle size of 6 micrometers. Another material was a composite made of clear untreated copper powder and a powder of titanium carbide system, which contained around 23% of titanium carbide, which obtained by high voltage electric discharge treatment of this titanium power in volumetric multi-spark discharge mode at a specific energy of 12 megajoules per kilogram. Also, we performed treatment of mixture of the powder of composition, which had a composition of 90% copper and 10% titanium in different modes, which we performed variation of specific treatment energy in range from 5 to 12 megajoules per kilogram, and also we performed the variation of modes. So we realized, as I said, single discharge with more mechanical impact, and we realized volumetric multi-spark discharge with more plasma and heating treatment. As we have shown before in some of our publications, when we perform treatment in kerosene and other hydrocarbon liquids, we can achieve not only the grinding of treated powders without their oxidation, but also such treatment leads to the synthesis of nanocarbon particles, which can include fullerenes, and the quantity of these new carbon phases is directly proportional to their specific treatment energy. And this was studied for titanium powder, but our results for different compositions shows that general relationship remains the same. It's the more energy we release in the liquid, the more is the total quantity of different carbon-containing compositions, including carbides. And as the results of a high voltage discharge treatment of powder mixture show, such treatment in all studied modes allowed us to grind select powders, which allowed us to decrease the medium diameter of treated powder mixture from 36 micrometers to around 8 and less micrometers. Also, when we perform treatment in single discharge mode, such treatment leads to some increase in the volume of spherical particles, while for volumetric multi-spark discharge, there is no clear relationship between the increase of treatment energy and the fraction of spherical particles. Here you can see the properties of our reference composites, which we used to first test our approach, so that the addition of titanium carbide to the copper matrix can lead to formation of metal matrix composites which could be used for electrodes, and also use them for reference. And here we can see that these composites showed the increase of strength both for clear titanium carbide and for mixture of titanium and titanium carbide obtained after voltage electrodischarge treatment of titanium powder. But we can see that the resistance of such composites was not as good as we expected, because their resistance was a little bit less than for clear copper. But here we can see that heat resistance increased as we increased titanium carbide content in the copper powder. In the composition of the obtained metal matrix composite, heat resistance increased. And here you can see the properties of metal matrix composite obtained from powder mixer copper titanium treated by high voltage discharge in kerosene in spark discharge mode. Here we can see that in range from specific specific treatment energy range from 0 to, without treatment means 0 is for initial copper, from 0 to 10 megajoules per kilogram, we can see that hardness almost remains the same, but as we increase specific treatment energy, which increases the carbon contained phases content, we can see the decrease in the hardness of these materials. While specific electric resistivity of these materials sees sharp growth, and then it slightly decreases. And here we can see that treatment with 10 megajoules per kilogram allows us to obtain metal matrix composites, which has wear resistance higher than for initial copper, with the relatively same hardness. It slightly decreases, but it can be considered they are the same. And here also we can see that this composite has a very high heat resistance compared to the heat resistance of clear copper. But the results for the treatment of copper titanium powder system in volumetric multi-spark discharge showed slightly different results. Here you can see hardness values for some composites in the range of 0, and this means that the specimens were destroyed during hardness testing. So if we perform treatment with specific treatment energy above 10 megajoules per kilogram in this mode, this leads to the synthesis of large quantities of excess carbon phases, which leads to the formation of composites with very low strength. And also here we can see that even the composite which was obtained in the mode with 10 megajoules per kilogram, it has relatively low wear resistance compared to clear copper, and also it has less heat resistance. So this allowed us to use our technological scheme for synthesis of metal matrix composites of different composition for the case of synthesis of copper titanium carbon composites. As I said, it consists of 2 stages, first of which is a treatment of initial powder mixer by high voltage discharge in kerosene, and the second stage is spark plasma sintered, which allowed us to obtain high quality metal matrix composites with decreased self-cost. So as the main conclusion, our treatment allowed us to obtain a very resistant metal matrix composite of copper titanium carbon system, which contains different phases, including titanium carbide and carbon, and in some cases it's also contain a titanium copper intermetallic compound, which has wear intensity almost 2 times lower than for consolidated sample of initial copper, which has a slightly higher specific electrical resistance, so we get a trade-off. We get a material for electrodes, which costs less, which lasts longer, but it has slightly higher electrical resistance. So thank you for your attention, and I also would like to thank organizers for the opportunity to show the results of our studies, and also I would like to thank the Armed Forces of Ukraine for providing us all the opportunity to actually gather and talk with each other. Thank you for your attention.
Questions to Andrei Terpakov and his work? No questions? Okay. I have a question. It's your synthesis of carbide phases in kerosene. It's a reproducible technology from one probe to other.
Yes, we studied synthesis of titanium carbide for clear titanium powder. It was shown in our previous works, and so we can see that this curve, which I showed for carbon-containing composites, the quantity of titanium carbide, it has not the same volumes, yes, but it has the same character. So we can see that increase in specific treatment energy leads to the increase of quantity of titanium carbide. But the only problem is that for titanium powder, it is greatly reproducible, and for different powder compositions, there can be some problems because as well as excess carbon forms carbides, it also can stay in the form of amorphic carbon, which is not good for the properties of composites. So yes, this is repeatable, but different treatment energies could be advised for different combinations of materials in powder.
Thank you. And the final speech of Yuri Baki, titanium carbide alloy self-lubricating tool steel Bokra. Yuri Baki is present or not? Okay, he's not present, but we have a speaker, Tatiana Solntseva.
Sorry, we are present. I could not
present?
unmute myself. Sorry.
Okay. It means that start your presentation, please.
Yes, I will share my screen.
Yuri, but Zahar. Okay.
Yes, my name is Zahar Boki. I will present instead of Yuri. Good afternoon.
That was agreed upon.
Yeah. Good afternoon, ladies and gentlemen. My name is Zahar Boki. Today, together with the author, inventor, and steelmaking production engineer Yuri Boki, and in collaboration with our colleagues, we would like to present our technological development of an innovative tool material, titanium carbide alloyed self-lubricating tool steel Bokra. Recent advancements in mechanical engineering and machining have led to widespread adoption of automated systems, including computer numerical control machines and flexible manufacturing systems, which heavily rely on metal cutting tools for parts fabrication. The increasing demands of these automated systems necessitate specific requirements for cutting tools, prominently featuring enhanced durability of the tool material. This directly impacts tool longevity within the unique operational conditions of automated production. The most common groups of tool materials used for cutting tools are tool steels and hard alloys, cemented carbides. However, materials within these groups do not simultaneously possess high physical, mechanical, and cutting properties. For instance, despite their high hardness and durability, hard alloys exhibit low impact toughness and are difficult to machine and deform. While more robust, tool steels are more ductile and readily machinable, but their relatively lower hardness results in significantly inferior durability compared to hard alloys. The primary causes of cutting tool failure are frictional forces and the heat generated by cutting forces. Friction leads to tool heating, softening of the cutting edge, and accelerated wear. Therefore, the development of a tool material that simultaneously possesses high hardness, wear resistance, sufficient toughness, deformability, and a reduced coefficient of friction represents a pressing challenge for material scientists. Leading researchers worldwide have addressed the challenge of developing advanced tool materials. A known approach involves the synthesis of steel and hard alloys, aiming to combine their respective advantages, the processability of steels and the high durability of hard alloys. Composite materials such as ferro-TiC, USA, and ferro-titanite, Germany, were developed, in which titanium carbide, 45% by volume, is bonded with a steel matrix. While these materials partially address the stated problem, they do so incompletely. They are machinable, but remain non-deformable. exhibit low toughness, and lack the required cutting properties.
Dear Zahar, I want to ask you why you show us some illustration on the Russian language. It's not possible on this conference. This conference official language is English, and it's you demonstrate some not.
Yeah, I'm sorry. Yeah, this was just for illustration. This is materials from the development phase, which took place in 80s and 90s. So
it's not novel, and it's not possible for this conference and in this country. If you understand why I stop your speech, because this night was for all people in Ukraine not very good, and you demonstrate some data and etc., and it's not appreciable. Okay, continue.
yes, there is everything follows is in English only. So sorry for that. So these materials are machinable, but remain non-deformable, exhibit low toughness and lack of required cutting properties, making them unsuitable for manufacturing cutting tools. Furthermore, the processes occurring during the sintering of titanium carbide with the intrinsic carbides of steel binders have remained largely unexamined. The aim of this study is to develop a novel tool material by synthesizing a commercial-grade tool steel with titanium carbide, and to instill the anti-friction properties by introducing solid lubricants into the composition. For the experimental investigations, the following materials were utilized: nitrogen atomized powders of high-speed steel R6M5K5, 1.3243, and die steel similar to 1.2581. Titanium carbide powders produced by various methods, including carbothermal reduction and pseudofusion. Solid lubricant powders of molybdenum disulfide and hexagonal boron nitride. Results. Microstructural analysis of samples sintered with titanium carbide produced by different methods revealed the following. In samples fabricated using carbothermally reduced titanium carbide, the steel matrix exhibited an absence of intrinsic steel carbides, figure 1C. Carbide forming elements from the matrix had diffused into the TIC, forming a distinct rim with an intermediate carbide, titanium vanadium C, at the steel TIC interface. X-ray diffraction analysis confirmed that the lattice parameters of this intermediate TVC carbide were within the range of values observed between titanium carbide and vanadium C carbides. Consequently, the steel grains were depleted of carbide-forming elements, leading to a reduction in the quantity of intrinsic steel carbides, a decrease in particle microhardness, and deteriorated durability. In contrast, samples prepared with pseudo-fused titanium carbide obtained via direct synthesis of titanium with carbon retained the original structure of the steel matrix, including the presence of its intrinsic carbides. Moreover, the matrix maintained its hardness, figures 1A and B. In samples with pseudo-fused titanium carbide, intrinsic carbides are present within the steel matrix, appearing as fine white inclusions on a dark and white background. In contrast to the amorphous particles of carbothermally reduced TIC, pseudo-fused TIC exhibits a crystalline particle form with a smaller specific surface area. Pseudo-fused titanium carbide is primarily used for abrasive materials and was considered unsuitable for applications in steel-bonded composites due to its low activity. But in this particular case, this property of pseudo-fused titanium carbide proved to be crucial for obtaining a steel TIC composite that possesses cutting properties and is suitable for manufacturing cutting tools. The successful preservation of intrinsic carbides within the steel matrix allowed for the selection of a composition with a significantly lower titanium carbide content compared to analogous materials. Even with the addition of 20% by weight, approximately 30% by volume of titanium carbide, the material achieved the target hardness comparable to that of hard alloys like VK8, HG30, reaching 70-72 HRC or 87-90 HRA. Further increasing the thick content up to 25% by weight resulted in only a marginal increase in composite hardness by approximately 0.5 HRC. The reduction in the amount of titanium carbide in the material became the second key aspect of the technology. This enabled the material to be deformed into long rods of various profiles using hot extrusion. Deformation significantly refines the material microstructure and substantially enhances its physical mechanical properties. While exhibiting comparable hardness to hard alloys, the developed material surpasses them in strength by 1.5 times, 220-260 MPa, and in impact toughness by 4 times, 130-150 kilojoules per meter squared. The deformed rods can subsequently undergo rolling to produce strips with thicknesses down to 1 millimeter. Following the laboratory investigations, extensive industrial trials of the new tool material were conducted, involving over 20 enterprises from the mechanical engineering, metallurgy, aviation, and mining industries. Approximately 40 types of variable tools were manufactured for these studies. This table shows the average test results for various cutting tools, including cutting plates, various cutters, 10 different types of milling cutters, and more. The tests were compared to various high-speed steels, including powder metallurgy produced ones. Based on the results of 26 tests, the durability of tools made from the new material exceeded that of conventionally produced high-speed steels by 3.5 times on average. When testing the new material against hard alloys, the durability of the cutting tools when machining difficult-to-machine steels was comparable to that of the hard alloys. During hot stamping, the durability of the stamping tools exceeded that of the hard alloy tools by more than 3 times. The second phase of the study investigated the influence of solid lubricant additives, hexagonal boron nitride and molybdenum disulfide, on the cutting properties of the novel tool material, with a primary focus on durability during cutting. The table presents the results of comparative cutting performance tests for the new tool material, composed of R6M5K5 steel plus 30% by volume titanium carbide, both with and without boron nitride solid lubricant addition. Tool life tests were conducted under various cutting conditions and on different workpiece materials. The experimental data indicates that BN solid lubricant additions enhance tool life during cutting operations by a factor of 3.3. The incorporation of BN solid lubricant leads to a reduction in cutting forces, consequently decreasing the abrasive mechanical wear of the cutting edge, lowering the temperature in the cutting zone, and significantly increasing the material's durability. This constitutes the third key distinguishing feature of the developed material compared to existing analogs and various carbide steels. The cumulative factor for the increase in tool life for the new tool material with solid lubricant additions is more than 10, 3.3 by 3.5. Based on the conducted research, the developed grades of tool materials for cutting and stamping tools have been registered under the trade name Okra steel. Additionally, technical specifications for the supply of these materials have also been developed. This graph shows the effect of the quenching temperature on the secondary hardness, the ultimate bending strength, the austenite grain size, and the hot hardness of this composite. Conclusions. Through the conducted research, a significant scientific and technical challenge has been addressed by developing a novel tool material with enhanced anti-friction and cutting properties through the synthesis of a commercial-grade tool steel and titanium carbide. Specifically, the following objectives have been achieved. It was established that during the sintering of the steel-thick composite, an undesirable migration of the intrinsic carbides from the steel matrix into the titanium carbide occurs, forming an intermediate titanium vanadium C carbide on the surface of thick. A method to minimize this phenomenon has been developed. The technical feasibility of deforming a steel titanium carbide composite with a total carbide phase content of thick plus matrix carbides up to 50% has been confirmed. Compositions and production technology for a new tool material, Bokra steel, have been developed. The material contains 90 times less tungsten than hard alloys for cutting and 35 times less tungsten than hard alloys for stamping, which should reduce the demand for this costly and strategically important material. The positive influence of solid lubricant additives on increasing the durability of materials for cutting tools has been established for the first time. Bokra steel is a deformable and machinable tool material that surpasses conventional tool steels in durability by 10 to 20 times and performs at a level comparable to or superior to hard alloys in many applications. Thank you for your attention.
Thank you. Dear colleagues, do you have any questions?
If I may, I have. Could you go to the previous slide to the conclusions?
Yes, sure.
So, in one of today's speeches, the interplay between the plasticity and hardness was discussed. That it is typically hard to have both. And in the point 5 of your conclusions, Bokra is posed as both deformable and better performing than hard alloys. Could you perhaps comment on that?
Yes, exactly, because usually the hardness and long tool life was achieved by high content of titanium in analogous materials up to 50%. I think it was 48 or something in one of the previous slides. And here, using the pseudo-fused titanium carbide, it was possible to just add 20% by weight or 30% by volume, which still kept the hardness and durability properties, but allowed for the material to be deformable and machinable. So this is one of the unique properties of it.
Okay, thank you. Thank you. That's great.
Okay, Vladislav, Billy.
Yeah, I have a question. Did you try to compare your material, Bokra material, with today maybe more new materials from, for example, Bosch with different coatings or other more new materials?
As to my knowledge, no, because main work was done as was said in 70s and 80s. And since a lot of certificates of author and patents were obtained, but no, we have not compared to recent developments.
And other small question, do you want or do you plan to make coatings for your instruments? And what this coating should be?
I would need to consult with my colleague. 1 second, please.
Okay, thank you.
We haven't, because the material already has such properties. Maybe some type of coatings can increase it even more, but that was not investigated yet.
Okay, thank you.
Thank you very much.
I think we finished this.
Thank you.
Finally, we have a reporter from morning, Tatiana Solntseva. Please briefly, quick report about your materials. 5 minutes. It will be, I think, enough because we spent our time and work without coffee break.
П'ять хвилин? Ну, я спробую. The study of evolutionary processes in non-equilibrium physical-chemical systems and the mechanism of the change of organized matter has become a control problem in modern natural science. Undoubtedly, understanding this process will enable target solutions to a number of common problems in various fields of science and technology, and most significantly, in the creation of new functional materials. To create new materials based on principles of biological systems, which maintain their non-equilibrium state due to the dynamic stability through the flow of negative entropy, specifically through the exchange of energy and matter with the external environment, it is necessary to establish nonlinear interaction mechanisms such as those observed in transition metal selenide compositions. The discrete nature of this composition allows for the formation of dissipative structures in localized regions and the stability of the composition as a dissipative object on a macroscopic scale. Until now, the stability of such systems has been associated with the emergence of self-oscillatory reactions and the outer wave processes they initiate. This raises the question of the nature of chemical affinity beyond the thermodynamic stability threshold of a non-equilibrium system. Therefore, the aim of the study was to more thoroughly elucidate the nature of the formation of dissipative structures as a consequence of self-organizing processes. To this end, interaction processes were studied in complex systems based on titanium with metals that have greater chemical affinity for elements of the oxygen group than titanium, for example, aluminum. Так. You can say us change slide. Да, please, number 2, slide number 2. Indeed, when decomposed in vacuum diselenide of metals of the 4th, 5th A and chromium do not completely release selenium. Не встигли. Не було енергії, і ми не встигли підписати. Давайте наступний, там українською буде. Далі. Добре. Пропустимо, да. When introducing diselenides as components into metal matrices, either based on the...
Пані Тетяно, я думаю, що тут у вас всі слайди російською мовою.
Українською.
Українською також не... Ось один слайд українською. Я думаю, що раз ви не встигли, буває таке, то наступного разу.
Скажу і все.
За 5 хвилин вкладетесь. Добре, тоді дуже швидко, 5 хвилин без слайдів, давайте так. Репорт, тому що люди чекають і вже ми перебрали час. Дякую.
It should be noted that the decomposition of diselenides and sintering results in the formation of compounds with increased stoichiometry. This is due to the kinetic properties of the products process and the catalytic properties of transition metals. The catalytic nature of the interaction between transition metals and selenium is demonstrated by experimental data on the non-composition of the gaseous medium using mass spectrometry analysis during the heating of crushed sintering composites. It was found that the gaseous medium is dominated by atomic gas, while the sintered medium releases a greater proportion of molecular gas. A study of the nature of the distribution of elements in the vanadium niobium selene system showed the existence of selenium compounds of different stoichiometries beyond the threshold of their thermodynamic stability. Slide 8 shows the region of stability or thermodynamic state of a number of sulfides and selenides of transition metals of group 4, 5, and 6A. The structure... Тут не висновки, тут еще... Так, борон... Сейчас. Boron carbide and boron nitrate were added to the VT14 system with molybdenum selenium 2. During sintering at 1250 degrees centigrade, active interactions occur forming borides, nitrides, and carbides of titanium and molybdenum. During friction of material, dry friction itself, a wide range of oxides, aluminum, titanium, molybdenum are formed, demonstrating the high dissipative capacity of this material. Diffraction pattern of the composition sintered at this temperature тоже shown in slide. Thermokinetic of self-assembling titanium-based material exposed to the thermodynamics of a self-assembling titanium-based material exposed to an external heat flux of the sample surface. The system is observed to enter the energy dissipation mode. We observe the system entering the steady state energy absorption. The introduction of refractory compounds into transition metal-based composition makes it possible to obtain dissipative structures with varying degrees of energy dissipation intensity and, as a result, control the heat resistance of materials.
Thank you. We continue with our discussion and continue with poster session. The first, Vitaly Sheremet with poster improvement of wear resistance, tungsten carbide 15 cobalt, cemented carbide tools subjected up to 400 MPa, high hydrostatic pressure after sintering. Please. Yes. 5 minutes, please.
5 minutes.
Thank you for letting me speak. Cold isostatic pressing is a well-known method for shaping and densifying products made from powder materials. The advantages of isostatic pressing are well understood. However, for the first time, we have demonstrated the potential of applying isostatic pressure to the processing of already sintered tungsten carbide-based cemented carbide products. The technology of processing sintered products under high hydrostatic pressure is not new. It has already demonstrated its advantages when applied to various materials produced by 3D printing, where the effect of high hydrostatic pressure was mainly limited to closing large pores. Nevertheless, the impact of high hydrostatic pressure on the properties and performance characteristics of cemented carbide products poses a more fundamental physical foundation, which was analyzed in our study. It has been shown that high hydrostatic pressure of cemented carbide containing 15 mass% of cobalt initiates a martensitic fast transformation in the binder phase, accompanied by a change in the dominant crystal lattice structure from face-centered cubic to hexagonal closed packed. Evidently, the martensitic transformation was triggered by interfacial stresses that arose at the boundary between tungsten carbide grains and cobalt binder due to the significant difference in their compressibility coefficients. Moving onto the mechanical properties, it should be noted that high hydrostatic pressure treatment resulted in a 10% increase in strength and a corresponding increase in Rockwell hardness. However, the effect of high hydrostatic pressure on the deformation behavior of the tool made of the treated material during operational testing was more pronounced. It was found that treatment of cemented carbides contributed to an increase in wear resistance during cold plastic surface deformation or burnishing process with a tool made of this material against 45 steel blank. It was shown that the measured wear parameter on the working surface of the burnishing tool that were subjected to high hydrostatic pressure was 30% lower than that of the tool not subjected to the treatment. The wear of the cemented carbide tool was not subjected to high hydrostatic pressure treatment, occurred due to the attachment of large clusters of tungsten carbide grains and cobalt binder together with an adherent layer of the steel workpiece material. In contrast, the wear of the non-treated cemented carbide, treated cemented carbide tool occurred through the gradual chipping of individual tungsten carbide grains. The higher durability of the treated cemented carbide tool was reflected in its ability to maintain a high-quality machined surface of the tool workpiece for a longer period compared to the tools that had not undergone high hydrostatic pressure treatment. Thank you.
Thank you. That finished in time. Okay. And we continue. The next, Tatiana Serebryuk, the impact of technological conditions on the structure and mechanical properties of composite materials based on aluminum nitride. Please. Start.
Good day. And aluminum nitride was used as the basis for creating new materials with high ability to absorb electromagnetic radiation and sufficient mechanical characteristic for the field of electronics. The yttrium oxide, zirconium diboride, and diamond powder were added to bases and mixed in a planetary activator. The composite materials were sintering by the hot pressing at a pressure of 15 and 12 megapascals are mod 1 and mod 2 respectively. The using X-ray diffraction analysis, it was determined that the structure of all composite materials contains the main phases. The aluminum nitride, aluminum oxynitride, zirconium diboride, zirconium carbide, yttrium aluminum garnet, and graphite. The matrix phase is aluminum nitride and is marked in gray in the same image, and its amount is 69 and 75% for mode 1 and 2 respectively. The less aluminum nitride in the composite structure made in mode 1 due to the formation of more aluminum oxynitride phase. The content of other phases present on the distribution maps is minimal and almost the same of both samples. The Vickers hardness measurement at a load of 49 newtons showed that hardness of the composites is 9 and 8.7 gigapascals. The slight decrease in hardness values is likely due to a decrease in the amount of aluminum oxynitride phase. The fracture toughness of the samples is almost the same. As we can see from the research results, the composite materials obtained at a pressure of 15 megapascals has a slightly higher hardness value, probably due to higher content of aluminum oxynitride in the composite structure. Thank you for your attention.
Thank you. The next will be Yuri Sirek, design and characterization of eutectic-based composite converters for LED, LD, white light sources. Please. Yuri Sirek, please start because 5 minutes.
Good afternoon, colleagues. Today I will present our recent work on the design and characterization of composite photoconverters based on cerium-doped eutectic composite of alumina and yttrium aluminum garnet and ruby for high-power LED and LD white light sources. Solid-state white light sources are rapidly developed due to their high efficiency, long operation lifetime, and environmental friendliness. A particularly promising approach relies on blue LED or LD pumping combined with the converter based on cerium-doped eutectic composite of alumina and yttrium aluminum garnet. This eutectic composite material stands out for several reasons. Its unique Chinese script microstructure enhances light scattering, improves heat dissipation, and supports stable operation under high power excitation. It also provides high luminous efficiency and thermal stability, making it attractive for next generation lighting. However, despite these advantages, this converter still suffers from insufficient emission in the red spectral range. As a result, their colored rendering index usually does not exceed about 70, which is a clear limitation for application requiring high color fidelity. To address this issue, we propose to combine this eutectic composite with a ruby plate. The ruby introduced an additional red emission band around 680 to 710 nanometers, thereby improving colored rendering without compromising the thermal robustness of the system. This composite design also allows us to tune the spectrum geometrically by varying plate thickness, instead of relying on co-doping, which often leads to luminescent quenching. Eutectic composite were grown by horizontal direction crystallization with cerium concentration up to 1 atomic percent. Ruby was grown by Vernel method with chrome concentration around 0.2 atomic percents. The two parts of each converters were joined using heat-resistance polymer design, ensuring mechanical stability and optical transparency at elevated temperatures. Two types of composite converters were fabricated, which different only in the size of the eutectic plates. The ratio of the area of eutectic and ruby plates in the composite converters was 1:1 in type 1 and 1:2 in type 2 converter. As a result, we got the chromatography coordinates of both converter types lie close to the white point region. Type 1 shows a shift towards warmer white, while Type 2 tends to cooler shades. Type 2 converters exhibit higher luminance efficiency and the color rendering index, with slightly lower colorated color temperature compared to Type 1. For instance, the configuration Type 2 converter with 0.3 mm ruby and 0.3 mm eutectic plates provides luminance efficiency above 170 lumens per watt, color rendered index around 79, and colorated color temperature near 6000 Kelvin. In summary, the cerium-doped eutectic composite of alumina and yttrium aluminum garnet is a highly promising base material for light converters, offering superior thermal and optical properties. By integrating with ruby in composite structures, we successfully improve color dynamics while maintaining high luminance efficiency. That's all. Thank you for your attention.
Thank you for your speech. We continue. The next, Denis Savchenko, symbiotic correlation between the concentration of paramagnetic centers on the interface surface of a composite based on pH halonitrile binderless and its mechanical characteristics. Please.
Dear colleagues, hello. Can you hear me? Can you see my screen now? I'm sorry, can you hear me?
Yes.
Yes. About screen, can you see my screen now?
Yeah.
Yes, thank you. So, if you allow, dear colleagues, please allow me to represent my poster report on the topic, which you have said about correlation between concentration of paramagnetic centers on the interface of composites based on phthalonitrile binders and its mechanical characteristics. The aim of this work was to develop a new method for modifying the surface of fibrous electrical conductive fillers based on electrochemical induction of paramagnetic centers on the surface of fillers. In order to create a thermostable and oxidation-resistant interfacial surface, and to enhance the performance of characteristics of composites based on high-temperature polymeric binders. Experimental correlation was confirmed between the concentration of such sinters, paramagnetic sinters, on the interfacial surface of fibrous materials, fibrous polymeric materials, fibrous field polymeric materials, and their mechanical characteristics, in particular the flexural strengths, the elastic modulus, and also the temperature dependence of mass loss. It was shown that such phthalonitrile oligomers combined with such fibrous fillers are suitable for creation and abrasive composites with high level of thermal and mechanical properties. Such composites are designed for using in products operating under extreme conditions. It was established that introduction of new method for modifying the surface of the filler can significantly improve such properties, as well as heat resistance and thermal stability of composites based on these polymers. Why did we do this research? Because in the recent years, we have targeted researches for developing high-strength polymer binders suitable for production of composites from superhide materials intended for operation under conditions for alternating mechanical stresses and elevated temperatures. Among them are diamond-containing tool composites and polymeric binders, wear-resistant anti-friction coatings, high-strength carbon fiber reinforced plastics for aerospace and rocket industry, and new polymers with multi-graphene structures exhibiting semiconducting properties. In particular, in the tool industry, long carbon fibers are an effective filler. Are effective fillers for manufacture of high precision diamond grinding tools. That's all. Thank you for your attention. And if you have any questions, I hope that I will be able to answer them. Thank you.
Thank you. The next will be Igor Krasikov. Effect of particle size distribution on multifractal properties of three-dimensional composite. Please.
The main topic of our study is the fractal properties of composite materials and how they are connected with the physical and structural properties of these materials. While working on this topic, we asked the theoretical question: do the particle size distributions affect the fractal properties? And if they do, how exactly? To find out, we made computer models of three-dimensional composites filled with spheres of different size distributions. We use the main types of distributions that are common in material science. You can see them in the graphs on the left. Since scaling does not change the fractal dimensions, we studied how fractal dimensions d0 depends on the ratio of standard deviation to the mean radius. The results for 10 and 20 volume percent of filling are shown in the graphs on the left. As we can see from this data, the fractal dimensions almost doesn't depend on the type of distribution when ratio is less than 1. But such high ratios don't appear in real powders. This result can be explained because for small values of this ratio, all distributions are very close to the normal one. The difference appears only when the ratio is large. This can be clearly seen in the graphs in the top right corner. So, main conclusion is that the fractal properties of a composite in practice don't depend on the type of particle size distributions and almost don't depend on the ratio of standard deviation to mean radius, at least for the values typical in material science. The second part of our study, shown in the bottom right graphs, is about the dependence of multifractal dimensions on the same characteristics. Here we look at the volume dimensions, blue, and the boundary system dimensions, red. The most interesting thing is that while for D0 the volume and boundary results are almost the same, for D1 and D2 they show very different behavior. We don't not yet have a mathematical explanation of this effect, but we are working on it and hope to explain it next time. Thank you for your attention.
Thank you for your report. And we continue. The next report will be from Andriy Patyuk. Formation of the structure of super hard PCBN composites in the cubic boron nitride, titanium nitride, aluminum system during high pressure reactive sintering.
BL Group superhard PCBN composites are tool materials with a structure contain 45-75% cubic boron nitride, where CBN grains size up to 3 microns are binder based on refractory compounds and are primarily intended for high-speed finishing or hardened steels and heat-resistant chromium nickel alloys. The load on the cutting tool blades is low, and tribochemical wear of the cutter predominates. The work investigated the formation of the phase composition and the microstructure of PCBN composites obtained by a reaction sintering at high pressure, 5 gigapascals, and temperature 1800 kelvins, of a mixture of CBN, titanium nitride, and aluminum powders with grain sizes less than 3 microns for CBN and 1.5 microns for titanium nitride and aluminum. The main objective of the work was to obtain microstructures where CBN grains are surrounded by a bond of refractory compounds of titanium and aluminum. The samples were studied using X-ray structural analysis and electron microscopy. Separately, calculation of the phase composition were performed based on the reaction balance in the mixture during reaction sintering, and the result of the calculation were compared with the phase analysis data. Analyzing of images of the composites microstructures obtained by electron microscopy confirmed that the CBN grains are surrounded by grains of the bond, which will protect them from tribochemical wear during tour operation. X-ray phase analysis showed the presence of 4 phases in the composite structure: CBN, titanium nitride, titanium diboride, and aluminum nitride. A comparison of the semi-quantitative XRD analysis data and the calculation can be seen on the slide. The quantitative phase composition determined using previously constructed calibration charts showed an underestimated amount of the aluminum nitride in the composites. Previous studies of the elemental composition of the mixture components for sintering using micro X-ray spectral analysis indicated the presence of oxygen and carbon in the non-metallic sublattice of titanium nitride. The calculation of the composites composition carried out taking this into account showed the presence of 6 phases: CBN, titanium nitride, titanium diboride, aluminum nitride, and possibly aluminum for carbon-free and aluminum to oxygen. Conclusion: the obtained composites meet the requirements for PCBN composites of the BL group in terms of microstructure and phase composition. Thank you for your attention.
Thank you for your report. In the next will be Alexey Kushev, influence of the graphite content on the topological properties of brass-based plasma coatings. Please. Sorry, it's Denis Andrющенko, synthesis of micro and nanofibers of silicon carbide by CVD method using iron coatings catalysts. Andrющенко нема? Oh. Denis Andrющенko, present? Absent? Oh, I say right. Please, Alexey Kushev.
Good afternoon. I present to you attention a research work, influence of graphite content on the topological properties of brass-based plasma coating. The work investigated the topological properties of plasma coating based on the brass L63. As a lubricate component using nickel-plated graphite and PG50 was added to the coating in amounts of 10, 30, and 58%. The nickel shell in the composite provides the required level of cohesion between the graphite and brass faces. High-speed steel T1 was used as counterbody material. The results showed that the friction pair L63 coating T1 steel exhibits the highest wear rate and coefficient of friction. The introduction of the nickel-plated graphite into the coating composition significantly improved the topological performance of the pair. Adding tin 50 weight percent and PG50 to the L63 braced coating reduced the linear wear rate and the coefficient of friction. The best wear resistance and thermal condition in the contact zone were observed. The coating contained 10 and 38% and PG50. Increasing the PG50 content lead to some deterioration of the topological characteristics of the pair. The study of the friction surface has established that for contains the tin weight percent and PG50 the sample surface. Exhibited relevant further damages area and minor region of material transferred to the counterbody. Increasing the PG50 content to 38% result to largest number of damaged zone on the sample and more extensive material transfer areas on the counterbody surface. This increase in the amount of nickel-plated graphite in the coating surface damage decreased and the warm areas became followed there were debris. At the same time, the material transfer to the counterbody was reduced. An increase in the content to coating elements and oxygen in the area of the friction zone indicates the formation of secondary oxide-based structure and suggest transition of the wear mechanism from adhesive to oxidative. In addition, graphite transferred to the counterbody was observed acting as a solid lubricant. This explains significant improvement in the topological characteristics when adding PG50 to the L63 coating. Thanks for attention.
Thank you. The next will be Vladislav Naumenko, development of elements for 3D printing by FDM from polymers enhanced with basalt fibers.
One moment.
Vladislav Naumenko, please start.
Do you hear me?
Yes, yes, of course.
Okay, thank you. Okay, I would like to present our research titled Development of Filaments for FDM 3D printing from polymers reinforced with basalt fibers. The motivation behind this study comes from the growing demand for strong yet lightweight material for 3D printing, especially in drone manufacturing. Conventional polymers such as ABS and polypropylene are easy to print, but they often lack sufficient mechanical strength. Therefore, we decided to reinforce them with basalt fibers and inexpensive and eco-friendly material known for its high strength and thermal stability. The aim of our work was to develop a filament based on ABS and polypropylene reinforced with a different amount of basalt fibers, and to study how the fiber content affects the mechanical and technological properties. To achieve this, we followed the process shown in the flow chart. First, it's the mixing the polymer and fibers in the sand one planetary mill. So second is the drying the mixture at 19 degrees Celsius for 1 hour. Third, extruding the material into filament using an exo extruder and 215 degrees Celsius. And four, then 3D printing samples by the FDM method with a Malian printer. We evaluated the filament's appearance, plasticity, porosity, and diameter stability, and finally tested printed the specimen for behind strength. The result showed a clear difference between two fiber contents. First, it's 2 white% when we added 2 white% basalt fibers. The filament became brittle, difficult to wind, and showed a poor adhesion to the printing platform. With 3 white% basalt fibers, the filament has had better flexibility, lower porosity, and stable diameter. In mechanical tests, the ABS plus 3 white% basalt fibers composite achieved the highest flexural strength, about the 16 megapascals, while still maintaining good printability. The graphs on the poster illustrate how this composition provides the best balance between strength and plastic deformation. To conclude, one, the addition of 3 white% basalt fibers to ABS and polypropylene composites provides the optimal balance between mechanical strength and printability. Two, increase fiber content to 10 white% leads to brittleness, poor winding, and adhesion problems during FDM printing. 3. The drying stage and 90 degrees Celsius is crucial for achievement stable filaments, diameter, and reduced porosity. 4. The ABS plus 3% basalt fiber composite demonstrate the highest flexural strength and good layer adhesion. 5. The obtained results confirm that controlled reinforced and optimized processing parameters significantly improve the performance of filaments for lightweight structural applications, such as drone components. And 6. Further research showed focus on enhancing interfacial bonding between polymer matrix and basalt fiber to improve touchness and print quality. Thank you for your attention.
Thank you. The next will be Irina Diduk, modification of basalt fibers for neutron radiation shielding properties in concrete composites materials. Please.
Good day, everyone. This research is to develop the new concrete composite materials reinforced by enhanced basalt fiber as a neutron-absorbing additive for spent nuclear fuel containers and biological shielding in nuclear reactors. Basalt fiber, derived from natural basalt rock, offers significant durability and is environmentally safe and non-toxic. Concrete reinforced with basalt fiber exhibits the following advantages: high chemical and corrosion resistance, longevity, high abrasion and shock resistance, high frost resistance. Due to its specific gravity, which is similar to the basic components of concrete, basalt fiber distributes evenly throughout the concrete mixture, unlike steel or polymer fibers. This property is particularly valuable in the nuclear energy sector, where long-term durability is critical. Structures as nuclear energy facilities, such as reactors and radioactive waste of SNF storage sites, require service lives ranging from 100 years. 4 types of enhanced basalt fiber were proposed and investigated: basalt boron fibers, basalt hafnium fibers, basalt yttrium fibers, and basalt gadolinium fibers. This type of fibers produced by adding oxides to the basalt melt. To assess the neutron and gamma radiation shielding properties using developed modified basalt fiber, a simplified model of practical transport through different layers of concrete from two types of SNF particle source was developed using the Monte Carlo codes Serpent, MCNP, and OpenMC. Neutron and photon transport from CNF sources was modeled through ordinary concrete to verify the developed model. Proposed concrete composite materials based on modified basalt fiber combines shielding properties and longevity suitable for NPPS and application, for example, safe storage of radioactive source and waste, neutron and gamma emitters. Thank you for attention.
Thank you. The next will be Katerina Kuznetsova, polymer-based nanocomposites with carbon nanorods for electromagnetic shielding, numerical study in the terahertz range. Please.
Good afternoon, dear colleagues. Thank you. The terahertz range is a promising area for ultra-fast wireless communication, medical imaging, environment monitoring, but the rapid growth of electromagnetic radiation rises the demand for efficient electromagnetic shielding materials. Polymer-based nanocomposites, especially those containing carbon nanotubes and other carbon fillers, are lightweight, flexible, and exhibit strong shielding performance. In this work, we numerically investigated the absorption mechanism of carbon roots and carbon tubes embedded in Teflon-based composites in the frequency range from 1 to 7 terahertz. Simulation were performed in COMSOL multiphysics using periodic unit cells with different geometries of fillers. The composite structure was modeled as a periodic array with carbon fillers with a period of 14 micrometers, substrate thicknesses of 6 micrometers, and with variable fillers sizes. Plasmon resonance was excited by a plane electromagnetic wave polarized along the long axis of the carbon roots. We varied several parameters: electrical conductivity, filler length, orientation and spacing, and geometry, rectangular roots, circular roots, and hollow tubes. First, we observed that reducing the conductivity of the carbon roots by 1 order of magnitude lead to a proportional decrease in absorption intensity. At the maximum conductivity, a stone absorption peak near 2.85 terahertz. Numerical modeling of electromagnetic field distribution and resonant absorption in the unit cell with two carbon roots was carried out to study how the spacing between identical or different sized roots affects near field interaction and overall absorption. By varying inter-root distance and element, we can precisely tune the spectrum, making it narrower or shifting it to lower frequency. Next, we compared different filler geometries. The absorption spectra and distribution pattern of electromagnetic fields in the unit cell were simulated depending on the size and type of carbon roots and increasing the root length of the curvature radius or band roots enhanced absorption and shifted the absorption peak. The shape of carbon fillers strongly affects the distribution on the local electromagnetic field and consequently the absorption efficiency. Round roots interact with the wave less efficiently because of their smaller surface area along the polarization direction. Hollow tubes have a lower conductive mass and weaker field localization inside. Overall, rectangular roots provide the strongest absorption performance due to enhanced change effects and larger interaction volume. In summary, the absorption properties of polymer carbon composites in the terahertz range are highly tunable by conductivity, spacing, and orientation of carbon fillers. Thank you for your attention.
Thank you. The next will be Igor Polyakov. Phase formation during synthesis of composite ceramic powders in metal silicon nitride system where metal groups 4, 6 transition metals. Please.
Good evening, dear colleagues. My name is Igor Polyakov, and let me present the result of the study of our teams on the topic which you see on the posters. So, the features of the solid phases interaction of components in powder reaction mixtures or titanium or zirconium or niobium or molybdenum with silicon nitride during vacuum heat treatment in the temperature range 800 to 1400 degrees Celsius have been established. In the presence of transition metal at temperature of 750-800 degrees Celsius, the dissociation of silicon nitride begins with the formation of highly active silicon and nitrogen. The result of the interaction of transition metals with silicon and nitrogen is the formation of silicide and metal nitrides through intermediate stage of lower compounds. The phase composition of the reaction mixtures at different vacuum treatment temperature is shown in the diagrams of section 2. The obtained experiment data could correlate with the calculations of the temperature depends of the Gibbs free energy for the equation of probably chemical transformation in reaction mixtures. You can see this on graph of section 1. For all the study systems, the formation of intermediate silicide or nitride phases begin in the temperature range of 800 to 1100 degrees Celsius, which when the processing temperature is increased to 1400 degrees Celsius, dissociate and completely disappear or remain in insignificant quantities. For example, in the system niobium with silicon nitride at temperature of 1100 degrees Celsius, the lower niobium is synthesis in amount of 28%, which remains stable up to 1300 degrees Celsius and completely dissociate when the temperature is increased up to 1400 degrees Celsius. You can see this as the third diagrams in section 2. A significant feature of the study systems is that at a temperature of 1400 degrees Celsius for transition metals of group 4, a series of fast transformation ends with the formation of mainly nitrides. It's titanium nitrides or zirconium nitrides. And for transition metals of group 5 or 6 with the formation of mainly of silicide. It's molybdenum disilicides or niobium silicides. They calculate and experiment patterns of interaction of the components of the studies mixtures at their stoichiometric ratio in the initial change studies in the work were take as the basis of the development of method for thermal synthesis of composite ceramic powders consist of silicon nitride and silicide or nitride of transformation metal of groups from 4 to 6. It has been established that for obtain the silicide powder systems, for example, molybdenum disilicide with silicon nitride by vacuum synthesis, an effective technology solution is to introduce an excess of silicon nitride into the charge relative to its stoichiometric amounts. For the synthesis of nitride silicide system, it's necessary to carry out a two-stage heat treatment of the reaction mixtures consequently in the vacuum and nitrogen atmosphere. This allowed obtain two-phase composite powders, which consist of for example, from niobium nitride with silicon nitride or titanium nitride, silicon nitride or zirconium nitride with silicon nitride. The described methods have been development for manufacture of homogeneous, finely dispersed composite mixture. And you can see this product on the section 3 scanning electron microscopy. And they obtained intellectual property rights. We obtained Ukraine patents from 2020 and 2024 years. Thank you for your attention.
Thank you. The next will be Pavlo Markovsky, microstructure and characteristic of titanium-based composites manufactured with blended elemental powder and 3D printing approaches. Please.
Thank you. This short communication is in a direct relation with my previous longer speech. And it demonstrates what is the difference between metal matrix composites of the same composition, but obtained by two different approaches. First, from left side, this is previously developed in our department, elemental powder metallurgy approach, when titanium hydride is mixed with master alloys powders with hardening particles into the green powder blend, compacted into powder preforms, sintered in vacuum, and because of rather higher residual porosity, usually it required additional hot deformation. The best results we received on hot isostatic pressure and absolutely dense material with high ballistic performance. And examples are shown on the another here, examples of microstructure. But when we used another approach, 3D printing using cored powder wires, we obtained a little bit another microstructure. What is the difference? Because in powder metallurgy approach required relatively long exposures during the sintering and, for example, for hot deformations, sub-sintering, hot deformation, such phases like titanium carbides in titanium matrix is not stable, and format intermediate solutions, final microstructure is relatively coarse. In case of 3D printing, even when materials go through liquid melted fast, interact because of very short period of exposure at higher temperatures, microstructure of carbides is much finer, very close to initial one, few micrometers. Due to these properties of such materials, especially ductility, is much higher. In case of when we used titanium barite, yes, of course, we introduced into green materials titanium dibarite. In the titanium matrix, it react with titanium, forming titanium monobarite. And in this case, titanium monobarite in titanium matrix is much stable from point of view of changing of dimensions. But also in case of 3D printing, this material, final material microstructure is much finer. And this is one of the main advantages of this method of 3D printing using our cored powder wires. Thank you for your attention.
Thank you. The next report, Ines Novoselova, effect of excess carbon dioxide pressure on the composition and properties of composite powders based on electrolytic tungsten carbide, please.
Good afternoon, dear colleagues. Over the last century, anthropogenic activity has led to a significant increase in the CO2 concentration in the atmosphere, reaching a record high of 41.6 gigaton in 2024. Therefore, efficient carbon dioxide utilization is a pressing scientific and environmental issue. Various approaches to its solving are possible: thermoelectrochemical, electrochemical, bioelectrochemical, and many others. We are working in electrochemical approach. It involves the electrochemical decomposition of carbon dioxide dissolved in a molten salt with production of solid carbon at the cathode and gas oxygen at the anode. This approach allows one to obtain different carbon-containing compounds, free solid carbon with various morphologies and structures, refractory metal carbides, in particular tungsten carbides, and in composites with carbon, with other metals, and mixtures of semi and monocarbides. In literature, this method is known as high-temperature or molten salts electrochemical synthesis. The schematic and advantages of it you can see in the introduction part of poster. Carbides were synthesized by electrolysis at temperature 715 degrees Celsius from 3 electrolytical baths pointed in the result part. The cathode products were analyzed by X-diffraction method, transition and scattering electron microscopy, thermogravimetric, and BET analysis. It was found, figures and table in the result part, that at CO2 pressure about 15 atmospheres or 1.5 megapascali in the system number 1, the composite of tungsten carbide and free carbon with particle sizes of 20-30 nanometers is formed. The content of free carbon in this composite does not exceed 3 weight%. Reducing the CO2 pressure to 7.5 atmospheres in this system resulted in the formation of mixture of semi-monocarbides. It was found that tungsten semicarbide has a homogeneous ordered polycrystalline structure resembling a 6-pointed star. The free carbon content in this case does not exceed 1 weight%. Adding lithium carbonate as additional carbon source for synthesis and reducing CO2 pressure, in this case up to 5 atmosphere in the system number 3, resulted in the formation of tungsten monocarbide with defective structure and lattice parameters other than standard ones, grain size of 10 nanometers, and fibrous structure, and an increase in free carbon content to 5 weight%. The specific surface area of carbide composite, depending on the CO2 pressure, can be varied from 20 to 140 square meters per gram. And in conclusion, CO2 control is one, but not alone, critical parameters which determine the phase composition, structure, morphology of electrolytical tungsten carbides. Another ones are current density, bath potential, and influence of these all parameters on properties of electrolytical tungsten carbides. You can see in the reference in our abstract. Thank you for your attention.
Thank you for your report. The next will be Marina Zamula, yttrium oxide effect on silicon nitride phase evolution and structural refinement via spark plasma sintering. Please.
Good evening. This study explores the formation of liquid phase in silicon nitride ceramics containing up to 10% silicon oxide with yttrium oxide additions, ranging up to 22 weight%. The characteristics of the spark plasma sintering consolidation, alpha-beta fast transformation in silicon nitride and mechanical properties are examined. The yttrium oxide content significantly influences consolidation, fast transformation, and the formation of silicon oxynitride and yttrium silicate. Without yttrium, silicon nitride exhibit poor densification. In silicon nitride with 1% yttrium oxide, 30 minutes holding at 1100 degrees results in an open porosity about 6. Increasing the yttrium oxide content from 3 to 7% significantly reduce the required holding time from 30 to just 5 minutes. At 15 and 22% of yttrium oxide, full consolidation is achieved in under 5 minutes. Fast analysis confirms that alpha silicon nitride appears only in yttrium oxide-free samples. It transforms into beta silicon nitride during SPS. In composition containing from 1 to 7 weight% yttrium oxide, approximately 50% silicon oxynitride forms, suggesting complete interaction between silicon oxide and silicon nitride through the yttrium silicate liquid phase. At 15 yttrium oxide, the silicon oxynitride content decreased to 20%, and at 22 weight yttrium oxide, silicon oxynitride formation is narrowly suppressed. Microstructural analysis reveals that all ceramics contain 2 micrometers elongated beta silicon nitride grains, with possible contributions from silicon oxynitride.
There is a distinct relationship between yttrium oxide content, holding time, and hardness, where from 5 to 7% yttrium oxide leads to optimal hardness and fracture toughness. This is associated with changes in volume of liquid phase, affecting formation of intergranular glassy phase. Liquid phase facilitates pressure-assisted desiccation through the rearrangement of nanograins and the dissolution precipitation of silicon nitride. Excessive levels can compromise properties. Thank you for attention.
Thank you for your report, and we will continue. Nadia Davidchuk, structure formation and consolidation of composite ceramics, titanium carbide, aluminum oxynitride. Please. Nadia Davidchuk, are you present? Okay. Continue. The next, Halina Krychkovska, visualization of fatigue damage in composite sucker rods based on analysis of the microstructure and fracture mechanism. Нету. Галина Кричковська, are you present? Okay, continue. Anastasia Lokatkina, high pressure sintered ultra high temperature tantal diboride based ceramics with silicon containing additives.
Yes, it's me. It's me. High pressure sintered ultra high temperature tab 2 based ceramic with silicon containing additives. It's a pleasure to present research result in this conference. I presented a poster of Anastasia Lokatkina. My name is Paulo Barvitsky. I also indirectly participated in this research and start. Transition metal deborides are promising for high temperature use due their thermal stability, hardness, conductivity, chemical resistance. However, tantalum diboride based ultra high temperature ceramics remains relatively understudied. According to literature data, the mechanical properties.
So sorry, but it claimed tantalum diboride, and here is hafnium diboride, and we hear your presentation earlier. Yes?
Yes.
You want to present again your presentation?
No, I want to present another presentation.
Ні, почекайте. Here is tantalum diboride. It's hafnium diboride.
I show it on my...
It's presentation. I'm not right?
See your new poster on your...
1 minute, we try to find the correct poster. Is this the last?
Can you see my...
Pavlo, could you please try sharing from your screen, because it seems like your two posters were a little bit
I'm sharing my screen.
What we currently see is Pavlo Barvitsky's poster, and the other one
I
was
share my
Kadmina.
new poster to you in Zoom.
It's okay. Thank you.
Open it full screen, please. Like Control L.
Not working.
Okay. Continue.
Oh, great.
According to the literature data, the mechanical properties of borate ceramic can be improved by adding silicides or carbides. This work presents the results of studies on the structure and mechanical characteristics Tabo 2 based ceramics with the addition of silicides, silicon nitride, molybdenum silicide, zirconium silicide, and silicium carbide sintered at high pressure, high temperature condition and by spa plasma sintering condition. In our work, high temperature Tabo 2 based composites were consolidated with silicon contained additives to lower sinter temperature and speed up densification. Mixtures were processed under high pressure, high temperature conditions at 4.1 gigapascals at 1800 degrees Celsius and 8 minutes, and in a receivable annual tight press. And under spa plasma acidic conditions at 45 megapascals, 8 minutes, 18 or 1900 degrees Celsius. Why did we use these additives? These additives partially react with Tabo 2 when heated, forming liquid fast or intermediate compounds. This reduces the sinter temperature by 1300 degrees Celsius and increases the density of the composite due to increased oxidation resistance. Such additives react to Tabo 2 to form new phases, which also improves diffusion and densification. Such additives also stabilize the structure by forming solid solutions, which additionally also increase heat resistance and mechanical characteristics. Additional such additives reduce specific weight too. In general, silicon-containing additives in Tabo 2 composites perform a dual role. They are sintering activators and phases that increase heat and oxide resistance, while strengthening the composite structure. It's almost ultra-high temperature materials are sintered at high temperature. For material base of tantalum duboride, this temperature is about 2200 degrees Celsius. But using high pressures, we were able to reduce manufacturing costs by reducing sintering time and temperature. New fluid densification was achieved to tantalum bore-2 silicium carbide and tantalum bore-2 zirconium silicium system. The tantalum bore-2 with 30% mass persons silicium carbide composite showed weakest hardness nearby 36 to 45 gigapascals. It was the best our results for our composites. In the end, we studied the consolidation condition, mechanical characteristic, and structure of composite based on tantalum duboride with the aim to creating special products. Such composites should replace construction materials based on hafnium duboride, which cost in 4 times greater than tantalum duboride. The main material will be prepared by hot pressure in future, but also considered investigation the possibility of consolidation under high pressure. Thank you for attention.
Thank you. And the next will be Roman Litvin, the system of silicon nitride, titanium nitride composite ceramics with 2D molybdenum selenide nanomaterial as a solid lubricant for tribological applications. Please.
Natalia will be presented this poster.
Okay. Represent poster.
The work intends to tackle the problem of durability and reliability of friction units, which are used in high-speed applications, such as jet engine, turbine engines, and helicopter transmission under adverse conditions. The concept involved the development of two-dimensional molybdenum diselenide nanoparticles, solid lubricant, interloper on the very resistant silicon nitride, titanium nitride ceramic substrate. This ceramic was used as one of the promising systems for obtaining wear and corrosion-resistant products. The aim of the work was to fabricate silicon nitride, titanium nitride ceramic dense samples using spark plasma sintering and to apply a surface layer of 2D molybdenum diselenide nanoparticles as solid lubricant. Composite powder intended for the fabrication of a very resistant ceramic substrate was obtained by thermal synthesis from a reaction mixture. You can see on the left illustrations on the poster. It's micron-sized silicon nitride and submicron-sized titanium nitride of 17 volume percent. Figures on the left illustrated the typical structure of sintered material and the distribution of chemical elements determined by SEM and ADS analysis. Figures on the right illustrated 2D molybdenum diselenide powders which were obtained by our own laboratory technology using chemical vapor deposition and investigated by X-ray analysis full profile result method. According to this data, the anisotropic nanoparticles with average sizes, you can see 5.2 nanometers and 27.3 nanometers in crystallographic directions 013 and 110 respectively. The ultrasonic and these nanoparticles were homogeneous and impurities free. The ultrasound treatment cavitation modes of two molybdenum diselenide nanopowders with ceramic dense samples was carried out in ethanol for 1 hour, followed by air drying and annealing. So the average thickness of molybdenum diselenide layer on the ceramic substrate was up to 20 micron by gravimetric analysis, depending on treatment conditions. So the samples of silicon nitride, titanium nitride ceramic coated with 2D molybdenum diselenide nanoparticles as solid lubricant were obtained for the further tribo testing. And we show a tendency to fill pores and microcavities of the ceramic surface by molybdenum diselenide nanoparticles. Which should be accompanied by the effect of lubricant retention in the micron relief covers during friction. I must say the study was supported by the NATO SPS program contract you can see on the slide in the end, and the agreement with the Ministry of Education and Science of Ukraine. Thank you for your attention.
Thank you. And finally, the bonus speech from Ivan Luzhny, electronic structure of triclinic tungstate, cuprum tungsten oxide, experiment and theory. One. One. Hello, everyone. Yeah. Translate. Complex experimental and theoretical studies of the electronic structure of copper tungsten oxide with formula present in the slide, crystallizing in the triclinic crystal structure, reported in the present work. In particular, for the experimental studies, we use X-ray photoelectron spectroscopy and X-ray emission spectroscopy techniques. While first principles band structure calculation of this compound are carried out within a density functional theory framework, exploring either a full potential linearized augment plane wave. Released in the Quantum Espresso program. The present experimental and theoretical data indicates that 3D electronic states associated with Cooper dominate the top of the valence band of triclinic oxide, where the main contribution of the tungsten 5D and oxygen 2p electron state on this tungsten state. In particular, the valence band maximum of oxide correspond to the gamma point, the center of the Brillouin zone, while the condition band minimum in the detector in the high symmetry Y point. Our DFT calculation indicates that the indirect band gap in oxide is equal to nearly 2 electron volts. This theoretical value is somewhat smaller in comparison with the experimental estimation of the energy band gap of triclinic oxide estimated to be equal to EG 2.3 electron volt and EG 2.06 electron volt. The present experimental XPS measurements indicate that the tungsten 4F energy core level spectra of the triclinic form are simple spin doublets with the binding energy corresponding to the formal valence state +6. The value is the binding energy of the XPS oxygen 1s core level spectrum in triclinic tungsten state is found to be close determined in double tungsten state. That's all. Thank you for your attention.
Thank you very much for your presentation. And we have last flash presentation is Dmitro Reznik, dual phase directionally reinforced high entropy ceramic composite.
Чутно. Алло. Good evening, dear colleagues. I want to present my report dual-phase directional reinforced high-entropy ceramic composite. The directionally solidified carbon borate with high-entropy debarites composite were prepared by the floating zone method based on crucible free zone melting of compressed powders, carbon borate, and powders of transitional metals debarites with technical purity were used as initial materials. The microstructure of all prepared alloys consists of carbon borides matrix uniformly reinforced by single-phase high-entropy debarites fibers and lamelles. You can see in the picture. The formation of eutectic structure, phase, and chemical composition and mechanical properties of directionally reinforced composites we investigated. The investigation of micromechanical properties of the obtained carbon borate with high entropy debarites composites showed that Vickers hardness H nu and fracture softness Chi1C are increased with growth rates 1 to 3 millimeter from 25 to 32 GPa and from 3 to 5 MPa respectively at load of 9.6 Newton. Which is higher than values of obtained of boron carbide-based eutectic alloys reinforced with individual debarites. The bending strength of prepared eutectic alloy is achieved up to 522 MPa. The results demonstrate an improvement in physical and mechanical properties. That's all. Thank you for your attention.
Thank you. Thank you for all participants for very interesting reports and participation in our session. And now I close the session, and the final speech will be from our organizer, Alexander.
Okay, dear colleagues, once again, we did a great job of moving through a week of discussion of our work and our achievements. This year, the event was to some extent an experiment. Ukrainian Materials Research Society was joined by organizers from 4 Ukrainian cities: Iron and Steel Institute of Nekrasov of the National Academy of Sciences of Ukraine in Dnipro, Institute for Single Crystals of the National Academy of Sciences of Ukraine in Kharkiv, Institute for Problems of Material Science, and Igor Sikorsky Kyiv Polytechnic Institute in Kyiv, and Karpenko Physical Mechanical Institute of the National Academy of Sciences in Lviv. Thematic symposia were running in those cities, sometimes even in parallel, and were streamed both to the Frantsevich Institute for Problems of Material Sciences, where additional discussion was possible, and also on YouTube. In my opinion, which I think other organizers share, we can claim a success with this experiment. Yes, there are things to work on for the next edition, but overall the event was very successful. Of 216 abstracts registered for the conference, 193 were delivered. And considering the wartime situation in Ukraine, I think, in our opinion, it's an excellent outcome. The talks were delivered by the speakers from Japan, China, Georgia, Lithuania, Romania, Poland, Austria, Serbia, Germany, Italy, France, the United Kingdom, the United States of America, and of course, from Ukraine. We are very happy to have such a diverse international community around this conference, and happy to see it growing from edition to edition. This successful event was brought to you by a dedicated team, both in scientific committee and organizing committee. And I invite all of you to visit the conference website and know a little bit more about these people. I think I won't overstep if, on behalf of the conference participants, I will express our sincere gratitude to the people involved in the conference organization. Thank you very much, the great and dedicated conference team. Let me express a wish of sorts, that in 2 years, the event will be even broader, perhaps involving more organizers and more symposia, even more interesting talks and discussions. And we will meet offline, even if in several Ukrainian cities simultaneously, in peaceful and recovering Ukraine. Let me wish all of you all the best in your work and life. Looking forward to meeting you at the next edition of HighMatTech conference. Thank you very much and take care.